So live streaming has also started.
So what is this YouTube link? You have a link, or I can search it?
So it will be on the, so if you just go to e-SMYIM YouTube page,
I see.
show up.
Let me try. I have never seen how it looks in YouTube. Let me check.
It looks identical to what is shown in Zoom.
Okay.
But yeah, try and let me know.
Yeah.
So Alok, do you want to put this on the e-SMYIM webpage maybe? Looks like it's not there.
This is the live now.
Looks like it's not there. Looks like it's not there.
Good morning. Yes, sir.
Looks like it's not there.
Good morning. Yes, sir.
Alok, I'll just be back in 1 second. I'm changing my internet connection. I'll be back in a second.
Yeah, that's fine. Good morning. Yes. Morning. The last session is usually always the interesting session, a bit challenging always. But we have had a pretty good turnout, I think, overall for the conference, and
Yeah, it went to 50, but generally it was 30 to 40.
right. It's meant to be a small conference, so I guess the good thing is people have gotten to know each other, and we have our next year's SMYM also will happen.
Yeah. Yeah, it went to 50, but generally it was 30 to 40.
Right.
Okay. No. Alok, someone is playing it on YouTube.
People have gotten to know each other.
Alok, if you're playing it on YouTube, you can actually mute your YouTube thing. So I have done the same.
Okay, that's why I heard the same thing. Okay.
Yeah, I was wondering why she's saying the same thing twice.
Even Alok has said hello, good morning many times.
Is it me who was playing?
I think so.
Oh. Okay, I see. So typically in this physical meeting, it would be much more in terms of number participant.
Not much, like 70. No, last night was not 100.
No, it wasn't 100.
It wasn't 100.
Okay.
But definitely there were more organizers and more like people who are not presenting, no?
Right. So this time one of the problems that happened because of December is it started clashing with too many conferences that are going on at the same time. There are obviously there's Conflu, but then there's few international conferences which are also on complex fluids which are happening about right now.
Yeah,
So
there's one in Jaipur, right? They have an international soft matter conference.
Did you attend that?
No. Basa just sent us some link, and one of my students is putting up a poster there. There seems to be biennial, every alternate years they do that.
It's 902, so I think maybe it's a good 17 participants. So I think and this number will hopefully rise very quickly now. So I think we should start now. So what I will do is I'd like to invite the section chair for this particular session, which will be Professor Kaushik Vishwanathan. Professor Kaushik Vishwanathan, he is a professor, assistant professor in the Department of Mechanical Engineering at Indian Institute of Science. He specializes in well, quite a few things, including manufacturing of soft materials and other types of soft materials. So I think we have a pretty good session chair in him. So with that, I'd like to invite Kaushik for chairing the session, please.
Thank you, Alok. So good morning, everyone, and welcome to the final session in this year's SMYIM. We have, I think, all our speakers here. We have 5 talks scheduled for this session, and it'll run from 9 a.m. until 30 a.m. So I think the links for the YouTube are also shared in the chat box. So if you have trouble with Zoom, you're welcome to use that link and follow on YouTube Live. So our first speaker in this session is Dr. Shubhadeep Mandal from IIT Guwahati. His slide is visible, I hope, to everybody. So please join me in welcoming Shubhadeep. You have 20 minutes. We'll have 5 to 10 minutes for questions at the end.
So thank you, Kaushik. So I am Shubhadeep and I am going to talk about microswimmers in nematic liquid crystal. So I would like to thank the whole team for giving me this opportunity to present my work. So a part of this work I did during my postdoctoral studies in Max Planck Institute for Dynamics and Self-Organization. So microswimmers are self-driven units. They are also referred as active particles or self-propelled particles. So these microswimmers are capable of converting their own energy or ambient free energy into systematic movement. So there are 2 different classes of microswimmers. One is biological or natural microswimmers. Usually they have flagella or cilia, and due to movement of those appendages, they survive and move in the fluid medium. Note that this kind of swimming motion of biological microorganisms or microswimmers are key to their survival and reproduction. Researchers have also developed artificial or synthetic microswimmers. So usually they don't have any moving parts. So a generic class of such artificial microswimmers is Janus colloids. So these colloids are made of 2 different types of surfaces. On the left, you can see a Janus colloid. So let me use the PowerPoint, the laser pointer. So this has 2 surfaces. One surface is inert and another is catalytic. So the catalytic surface reacts with a solute and produces a reactant, and it induces a concentration gradient. So this kind of self-induced concentration gradient or self-induced temperature gradient or self-induced electric field can lead to motion of these Janus colloids. So these are referred as self-phoretic or autophoretic motions. So we are interested in microswimmers because there are several potential biomedical applications, starting from transport of cargo to sensing, imaging, and microsurgery. So in many applications, these microswimmers are found in complex environments. The environments can be, say, blood capillary or some organ. And these complexities in terms of environments can be of 2 types. One is geometric complexity due to the heterogeneous nature of the medium, or the fluid itself is rheologically complex. Maybe it is having some anisotropic viscosity or some elasticity in the medium. So there are few fundamental questions. One is to what are the effective ways in which we can self-propel these micro swimmers in complex environments, how to control their trajectory and orientation, and how to control the collective behavior of multiple micro swimmers. So I am interested in nematic liquid crystal, and recently there has been several experimental results that several researchers have reported. So on the left two movies, you can see that a P. mirabilis bacteria is carrying the top movie a passive particle, while in the bottom we see that bacteria is carrying yeast cell. On the right, you see B. subtilis bacteria swimming in a circular swirl. Note that this kind of directed motion of bacteria cannot be found in Newtonian fluid. And these flows or this kind of cargo transport is not due to any external flow or field. This is due to the anisotropic nature of the medium and also due to the elastic nature of the medium. So the motivation of our work is to whether this anisotropic medium can be used to guide the microswimmers. And we have mainly two objectives. One is to study different types of microswimmers in nematic fluid and see how the domain confinement can play a role towards guiding these microswimmers. There are two key challenges. One is to model the microswimmer and another is modeling of the fluid. Note that the fluid is a nematic fluid, which is a non-Newtonian fluid. So let's first look into this nematic fluid. So usually this nematic fluid is made of rod-like molecules. So on the left, you see a phase which can be found at high temperature or low concentration. So though the molecules are rod-like, but there is no long-range orientational order. And this phase is termed as isotropic phase. So this is similar to a Newtonian fluid. But on the right, if we decrease temperature or increase concentration, we can have a phase in which there is long-range orientational order. And this phase is termed as nematic phase. And this long-range orientational order leads to anisotropy and elasticity of the fluid. Note that for Newtonian fluid, the direction, the physical properties are direction independent. But for nematic fluid, this anisotropy is there. So viscosity will not be constant in all the directions. Here I have given few examples of nematic fluid. One common is this 5CB, which is an organic nematic fluid. And the second one is a biocompatible one. So if you mix disodium chromoglycate with water, so we can have a biocompatible nematic fluid. And most of the experiments that people have done use for bacteria using this biocompatible liquid crystal. Several biomaterials also show anisotropic behavior, such as collagen, cellulose, synovial fluid, and also biofilms can show anisotropic behavior, though they are not strictly shows say elastic behavior, but there is some anisotropy associated with these biomaterials also. Now, modeling of this nematic fluid is complicated as compared to its isotropic or Newtonian counterpart because of this presence of long-range orientational order. And this orientational order in its generalized form can be expressed by a second order traceless and symmetric tensor. So it is termed as Q tensor. So in index notation, Q is expressed here. So there are two terms here. One is S, another is N. So S is a scalar. It is referred as scalar order parameter, and it represents the degree of molecular orientation along N, where N is referred as director or director field. So N is the common axis along which molecules are aligned. And as this is a non-Newtonian fluid, the Navier-Stokes equation is also modified. So in the index notation, we see on the left the density times the total derivative of the velocity v, and on the right we see divergence of the stress tensor. So here stress tensor has three components. One is the isotropic viscous stress. So this one is also there for Newtonian fluid, and additionally we have two different stresses. This one, the first one is anisotropic viscous stress, and the second one is second is elastic stress. And these two are referred as orientation velocity coupling terms. Additionally, we also have continuity equation. So to solve this problem numerically, we have chosen this method called multi-particle collision dynamics. It is a mesoscopic method, and here instead of solving the continuum equations, the fluid is represented by point-like particles, and two key steps are performed. One is called streaming, another is collision. In streaming, the particles are moved ballistically, while in the collision step, we divide the domain into small cells, and at each cell, we perform an instantaneous momentum exchange. This method gives both aerodynamics and thermal fluctuations, and it was developed by Malivernets and Capral. So we take this method, which gives the Navier-Stokes kind of behavior with thermal fluctuations, and we modify this for pneumatic fluid. The basic idea that we have used is to assign these point-like particles some orientational order. And then we have developed a method, and we have published this method. You can see, for details, you can refer to this article. So all the technical details can be found in this paper. You may refer that. So next is to modeling of microswimmers. On the left, you see microswimmers, even the biological one, can be found in different shapes and sizes, starting from few micrometers to 100 of micrometers. So for example, this small one having multiple flagella. Here, this B, it shows a single flagellum, while this big one is a paramecium with cilia. So modeling of this biological microswimmers is challenging, but we have considered a rather simple model which was first proposed by Lighthill, and this model is referred as a Skurman model. So Lighthill proposed this model for ciliated organisms such as this paramecium. So this paramecium moves due to motion of small appendages. Those are referred as cilia. So the key idea is to have a cell body and some self-propulsion mechanism. So this Skurman model is nothing but a rigid sphere with prescribed surface velocity. So on the surface, these blue vectors represent the velocity that we impose on the surface of this sphere. So in this model, the surface velocity that we mention is there's Vs, which is a function of theta. So this theta is the polar angle measured from this orientation vector. So E represents the orientation of the Skurman, and we have B1 and beta, two important Skurman parameters. B1 represents the self-propulsion strength, while beta represents swimmer type. So usually we have two types of swimmers. One is pusher, another is puller. So pushers usually have their propelling apparatus at the back. For example, this E. coli bacteria. So the flagellum is at the back and the cell body is in the front. So their motion is like this. So they move the fluids away from the cell body along this axis. So the fluid will be moved away in the rear direction and also in the forward direction. And for the puller, it is completely opposite. So the self-propelling apparatus, so these appendages are in the front and they are basically pulling fluid from the front and from the back. So these two can be modeled by simply changing the sign of this parameter beta. So negative beta means pusher, while positive beta means puller. So here I have given the schematic. So first we develop the pneumatic MPCD method, which is nothing but the MPCD method for pneumatic fluid. And then we couple that method with a moving Skurman. So this yellow color circle represents that Skurman. And this Skurman dynamics is solved using a molecular dynamic scheme. And this whole method is termed as pneumatic MPCD MD method. So in this schematic, you see the small lines represents the director vector. So the bulk director field is along the vertical, represented by this N vector. This is the MPCD representation The fluid is represented by these small black dots. So these are fluid particles. And to satisfy the no slip condition, additionally, we also need virtual particles represented by these red dots. And at the surface of the skimmer, we impose homeotropic anchoring condition. So this is nothing but the orientation of the nematic molecules perpendicular to the surface. With this, first we study the dynamics of pullers in a periodic domain. So these lines does not represent the domain boundary. These are simply guide to your eyes. So in a periodic domain, if we release a puller type skimmer, then we see that at steady state, it always moves perpendicular to the director. Note that the director, the bulk director field is vertical, and irrespective of the initial orientation. So here initially it was placed perpendicular to director, here at some 45-degree angle, and here parallel to director. In all these cases, finally we see that the puller orients perpendicular to the director field. For pushers, it is completely opposite. We see that the pusher is moving parallel to the bulk director field. And this result compares with the experiments. So the experiments that was performed previously using E. coli or B. subtilis or P. mirabilis bacteria, these are all pusher type bacteria. And they have found that those pusher type bacteria move parallel to director field. Now, the question is why such reorientation happens. So Lintuvuri gave an approximate theory. So he obtained the torque acting on this skimmer, and he found that this torque not only depends on orientation and the bulk director field, but also depends on this skimmer parameter beta and B1. So by changing the sign of this beta, we can have nematodynamic torque acting on this skimmer in two different directions. So for puller it is clockwise, while for pusher it is anti-clockwise. Next, the main thing that we want to study is the skimmer in a confined nematic liquid crystal. So we insert two walls, the top one and the bottom one, and we also apply the homeotropic boundary condition as at those two walls. So director field is perpendicular to the walls. And here what we see, so we run simulation for different values of beta and B1. So these two are the key skimmer parameters, which signifies the cell propulsion strength and the swimmer type. And we see that so each marker represents a simulation data. And we see that there are three different regimes. So these blue triangles represent a steady swimming motion along the center line of the channel, while these green squares represent oscillating motion of the skimmer, while these red circles represent steady hovering state near a wall. So let's see. So we have found two steady states, one for pullers. So these beta positive values are represents puller type skimmer. So for puller, at steady state, the skimmer is oriented along the center line and it is moving along the center line. While strong pushers, these red circles, they are oriented perpendicular to the wall and they are not moving in the horizontal direction at steady state. Note that the bulk director field is vertical. So these two are the steady states that we have obtained. And now we look into two important dynamical quantities. One is the transverse position RZ measured from the bottom wall, while another is the orientation. So orientation theta s, it is measured from the vertical axis. So that here we see the variation of transverse position, which is normalized by the channel height. So this 0 value represents the bottom wall, 1 represents the top wall, and 0.5 represents the center line. And we see that, say, the blue line represents the puller, beta equals to 4, the positive value. And we see that even we have released this skimmer from the center line with an initial orientation of 45 degree, it moves slightly away from the center line, but finally settles at the center line. This is due to the fact that the nematodynamic torque is acting on it, and it is moved perpendicular to the director field. So director field is always vertical, and the schoolmark is finally moving along the center line. Now, another extreme is that beta equals to -4, this red line. This one is for strong pusher. So schoolmark goes away from the center line and settles at some position in between the wall and the center line. While for beta -2, this is weak pusher, the schoolmark oscillates. The same can also be observed in the orientation plot. So here schoolmark orientation variation with time is shown. So we see that the pullers released from 45-degree angle and it moves to 90-degree, and then there are oscillations. Note that these oscillations are due to the stochastic torque acting on the schoolmark, which are suspended in this fluctuating fluid. And for beta -4, we see that the orientation angle decreases and it goes to 0. So strong pusher is oriented parallel to the director field. And for the weak pusher, the oscillations are also quite prominent in orientation diagram also. So this also gives some comparison with experiments. So recent experiments with P. mirabilis bacteria, which is a pusher type, have given two important observations: that bacteria oriented approximately parallel to the director, and bacteria were dynamically positioned near the surface. Note that if this bacteria is suspended in a Newtonian fluid, then it will go very, very close to wall and it will stick to the wall, because there is one attraction, the aerodynamic attraction towards the wall. But in pneumatic fluid, they have observed that the bacteria was not going very close to wall, rather they were slightly away from the wall but positioned perpendicular to the wall. So here also we have observed that for strong pushers, the director field is vertical and the schoolmark was in between wall and the center line. Now the question can be that why can't the pusher hit the wall? It is not hitting the wall because there is wall-induced elastic repulsion. Note that the pneumatic fluid has elastic behavior, and that elastic nature.
Shubhadeep, sorry to interrupt. We have 5 to 6 more minutes, so we can leave some time for questions. Yeah.
So that elastic force usually basically resists the schoolmark to reach the surface. So in summary, we have developed a model which solves the pneumatic fluid using MPCD method. So the details of this method you can find in our published paper. And we have studied two cases. One is schoolmark in unbounded liquid crystal, and another is schoolmark in confined liquid crystal. And we have seen that the pusher moves perpendicular to director in periodic domain, while puller moves parallel to the director. And in confined domain, schoolmark can have steady or oscillating behavior depending on their values of B1 and beta, and schoolmark can settle at different transverse positions. Thank you.
Thank you very much. We have time for some questions. We have 5 more minutes. So
maybe I'll start with the question.
yeah, sure, go ahead, Alok.
So, Shubhadeep, very nice talk. It's quite interesting that in pneumatic fluids it changes so much. And a couple of questions regarding that. When you model the pneumatic fluid and when you are using the pneumatic fluid, I would like to know what type of pneumatic fluid it is and whether the fluid has any elasticity at all, or is it? So I think I sort of missed the portion where you're discussing the relationship. Is there fluid elasticity?
So the reported experiments in the literature, those were done using this water and disodium chromoglycate. So this is a biocompatible pneumatic liquid crystal. So bacteria can live in this medium, and there are several articles, mostly from the group of Oleg Lavrantovich from the Liquid Crystal Institute, Kent. So they have used extensively this biocompatible liquid crystal and studied bacterial motion.
Does this fluid have elasticity, or is this just a pure liquid?
Fluid has elasticity. So it has both anisotropic viscosity and elasticity.
Okay, and that you take that into account in your constitutive relationship, the elasticity. How do you take that into
Yeah,
account?
so I have not shown explicitly, but in the stress terms, there are three different contributions. The last one, this sigma E alpha beta, this takes care of the elastic term. So this depends on the this nematic orientational order. So this is a function of Q tensor. So there are relations. So basically this depends on the gradient of Q tensor. So if the nematic orientational order is not varying spatially, then elastic force is zero. But if it is varying spatially, then there will be some elastic force.
Oh, got it. Okay, great. Okay, thank you.
I have a quick follow-up on that question.
Yeah.
So this hovering happens, is that because of this elastic force, the same origin of the elastic force?
Yeah, so this
Yeah.
for strong pushers, yeah, we also developed one simplified theory in which we see that if we add that elastic force, then only the skirmer remains in between wall and center line. Because for Newtonian fluid, it will go to the wall and it will hit the wall.
And also when you had the fully periodic domain, right, in all four directions, there it was just going vertically up. That was the steady solution, right? So, okay. And does the Q alpha beta, is that also changed? Because there is no evolution equation for that, right?
Yeah, there is evolution equation. I did not show.
Okay, yeah. Okay.
There is a equation in which we have, let me show very quickly. Yeah, so this one is the evolution equation.
I see. Okay.
So it has three terms. One is the molecular field. It gives the alignment. So this can be obtained from the Landau-Digens free energy functional. And we also have velocity orientation coupling. That means velocity is also changing the Q tensor.
Oh, so it's fully coupled, is it? Okay.
Yeah. Additionally, we also have the stressless and symmetry constraints. But two key terms are the molecular field. This will give the alignment. And second is the velocity orientation coupling.
I see. Good.
I have a quick question if I can ask.
Yeah, please go ahead.
Thank you, Shubhadi. Very nice talk. Very naive question. What are the examples of what are pneumatic fluids? Like you gave example of bacteria and so on. So are any other fluids which are found in nature, pneumatic in nature?
Yeah. This 5Cb, this one is organic liquid crystal, and also this liquid crystal is also used in liquid crystal display devices.
Yeah, but like for example, you gave example of E. coli. So E.
coli itself is not pneumatic. So these bacteria are suspended in a pneumatic medium.
Yeah. So which of the fluids found in nature these are like okay, but I don't think these are found in the body or so on. So
in experiments, people have used this water and disodium chromoglycate. So this is a biocompatible liquid crystal that people have found, and starting from 2013 onwards, people are studying this bacterial motion in this medium. Because in other mediums, the bacteria will not live. So in this organic 5Cb or other mediums.
I see.
Yeah.
Oh, I think the question probably, if I guess it right, it came from the intro slide where you said it can be used for transporting the very first, right? You showed those three.
Yeah, I was just wondering that in naturally occurring medium, like how does this bacteria move and do the locomotion? Do they use the same? Do they use the same type of like whatever physics you have shown here, or is it something else?
No. In Newtonian fluid, let me show you a graph. Then it will be clear.
But blood is not a Newtonian fluid. It's there in blood. So how do they?
Those things are not yet investigated. Those are, so yeah, here you can see in the left bacterial motion in Newtonian fluid. So you see there is no strictly any directionality in the motion, but in pneumatic fluid they moves parallel to the director. So director is horizontal. So the difference is clear that for Newtonian fluid, there is no strictly any directionality in the bacterial motion, but that is there in pneumatic fluid. And bacterial motion in bloods and other biofluids, those are not yet investigated.
Okay.
Yeah. The problem is whatever artificial microswimmers that we have, they don't propel in blood. So they usually perform some reactions with the medium, and in most of the cases we need certain percentage of hydrogen peroxide and other chemicals, and that's why it is very difficult to have some swimmer that will propel in blood. Maybe we have to use some other techniques, so ultrasound or something else.
Okay, thanks.
Okay, thank you so much, Pradeep. That was a wonderful talk.
Thank you.
We'll now move on to our next speaker. Shri Harita Rautu, are you here? Maybe you can just share your screen and turn on your video too. Yeah, so next speaker is Dr. Shri Harita Rautu from IIT Gandhinagar, who's going to talk about large area micro. Oh, there's the screen. It's here. Yeah, go ahead.
Good morning, everyone. Thank you so much, Professor Alok and the organizing committee for this opportunity. This is the first time I'm attending this soft matter meet, and I'm quite happy to connect with all the people. So it's coincidentally today is the group. It's finishing 1 year of anniversary at IIT Gandhinagar. So I'll be talking today about the large area micro patterning of alumina by colloidal lithography. So before we get into the scientific topic, I just want to present an overview of our group just in one slide, and then we'll see what is the challenge that we are trying to answer and the approach that we have followed, and probably a couple of contributions into the field, and of course the key takeaways from the talk. So the Functional Materials Laboratory at IIT Gandhinagar in the Materials Engineering Department. So we are a interdisciplinary group. We work with powders in the dry as well as the colloidal state, typically ceramics and polymers. And we also investigate wetting and de-wetting phenomena, both with the traditional concepts like lotus leaf and also the slippery properties by biomimicking the Nepenthes pitcher plant. We work with a wide span of fluids, not just limited to normal pure liquids like water or oils, but we are also working currently one project. We have like 30 liquids we are investigating. Most of them are all the real life fluids, and the third one is a soft lithography. So both at polymers, for instance, by replica molding or hot embossing or spraying techniques, and for ceramics, primarily with the colloidal lithography. So the fourth one is a small part, which is also we try and see what happens to the friction coefficient and the wear mechanisms of these lubricated surfaces. So as you all know, everything is interconnected, and therefore it's a very much self-sustainable experimental group. So today I'll be talking about the one little part of the soft lithography. So definitely there are a lot of contributors and team members for this work that I'll be presenting today. So that's a part of my PhD thesis. So it was done at Switzerland, Empathun and EPFL, and here are the team members. So the funding came from the Competence Center for Material Science and Technology, as well as a couple of industrial partners. One is a watch company and the second one is a BOBST. So let me begin giving a short introduction about the several techniques that we already know for the ceramics. Direct laser ablation that we know, and definitely we also know about micro injection molding, tape casting, anodization. So in terms of direct laser ablation of ceramics, the typical laser fluences for the ceramics is like in the range of 10-15 joule per centimeter square, while in the case of polymers it is 1 or 2 orders of magnitude smaller. So that means in terms of energy and the money, polymers is better, while ceramics is much more cost intensive. Also the second thing is it can also have local phase transformations, because during the ablation we are removing the material by different mechanisms such as photothermal, photomechanical, photochemical. And if you go to anodization, not all kinds of geometries and shapes are possible. So that is another limitation. And if we go with the so-called photolithography with the tape casting, so tape casting, obviously you end up having ceramic tapes in the range of sub millimeter. So typically people have manufactured 100 microns, 200 microns, and a maximum of 500 microns. So if we wanted to, for instance, make large area patterning, which are also on a bulk specimens, not just films. And if you want to create any kind of shapes, not just pillars or regular patterns, but even if you wanted to, for instance, emboss a logo of the Indian Rheological Society onto your ceramics, how do we do that? And with a very good precision, how can we do that? So for that, we have taken commercially obtained ultrafine alumina powders, which are having a phase of alpha, and they are agglomerated in the as received situation. So we have added a dispersant, which is typically having 2 weight percent of polyacrylic acid and 98 weight percentage of water. So we have adjusted the pA at 10 by using ammonium hydroxide, so that this polyacrylic acid long chain molecules, they are essentially forming a brush like structure on the aluminum oxide. This is leading to electrostatic repulsive forces and the steric hindrance, and thereby causing the stability of the suspension. So this agglomerated slurry in the beginning, we still have to de-agglomerate by giving a mechanical forces. So we were typically adding alumina beads, which are in the diameters of 1 millimeter. So we roll it for almost 48 hours, do an ultrasonication, and also carry out a degassing step. And then we end up having a de-agglomerated slurry, which is ready to cast. Of course, if we dilute it, we can also characterize the particle size distributions by using disk centrifuge method, and the particles are in the range of 150 to 200 nanometers. So in order to carry out the slip casting, if you wanted to do a simple slip casting, or if you wanted to do a slip casting for the micro patterning, the viscosity have to be optimized accordingly, because you will understand in the later slides how the viscosity is going to be like one of the very important factors in the drying of your ceramic suspension. So like for instance, by changing the alumina solid fractions, you see here that the viscosity is obviously changing with increase in the solid fraction. So for a higher solid fraction, the viscosity is higher, thereby the degassing and the de-agglomeration was not completed. So we ended up having macro holes on the surface. So that's a confocal microscopy image. And when we looked at the scanning electron microscopy images, so this is a typical hole that you see. And when you look more closely into the hole, you actually have a bimodal pore distribution. So there are pores which are almost like 5 microns or so, and there are also pores which are like 30-50 nanometers. So so the optimized viscosity that we found out was around 10 millipascal second. So for this particular solid fraction, alternatively, you can also do a more severe de-agglomeration by doing, let's say, not soft rolling, but let's say do a more hard rolling. That means you can give more energy to the beads that is doing this, that is breaking the agglomerates. So now the slurry that has been optimized to have the de-agglomerated situation, that we can use it for slurry casting. But how? What do we do before we cast onto the slurry? So the laser ablation, typically for people who do not know, so there are like we can classify it into two things. One is that if you have a long pulse laser, that is one shot is having a time of microseconds. So in such a case, you are melting the material, removing it, but it is also some of the material is casting back onto the the melted regions, as well as on the surface, it can lead to a lot of debris, and there might be also some damaged surfaces. While in the case of the ultra short pulse lasers, typically in the nanoseconds or the femtosecond lasers, it's pretty much a clean process, and you don't see a lot of debris. So we have used the ultra short pulse laser, which is a nanosecond laser, and it's a krypton fluoride based laser. So the master templates are polycarbonate sheets. Here in this figure, you actually see that it's a very long sheet. The length is almost like 1.3 to 1.5 meters, and the width is almost like 0.8 to 1 meter. So it's a very huge area. So that's also that comes from one spin-off company, Crealus, at Empathun. So and the ablation rate can be very nicely controlled based on your fluence energy. So if you have a small fluence energy, then your ablation rate is also small. That, what does that mean? So you are able to ablate 20 nanometer of the surface for a one particular shot. That is actually helping us to have a very good depth precision of the microstructures. So we take this master template and do a replica molding onto the Silgard PDMS, and we obtain the negatively patterned PDMS specimens. So here is one thing, the most key finding is that until that time in literature, people have been often using PDMS thick templates like almost like 1.5 to 2 millimeters and sometimes even 3 millimeters. However, in our work, we have seen that if you go down to sub-millimeter range, 400 microns, 300 microns, 500 microns, that is actually very good for drying, and we will ultimately end up creating bulk specimens where one side of it can be nicely patterned. So we will get to the scientific aspects of it, but this is, let's say, the technical difference between the literature and our work. So the slip casting, what exactly is a slip casting? So you have your ceramic slurry or suspension, and then you have open molds. So the open molds contain these cavities. These white ones are essentially the regions where we pour our slurry. And below this mold, we have added a cellulose nitride based filter paper that will prevent the sticking of your slurry to the base. So the base is made of a plaster of Paris. So plaster of Paris is nothing but calcium sulfate .05 water, and it can take more water and become gypsum. And of course, gypsum can again be converted to plaster of Paris by heating to 100 degrees Celsius and then letting all the water go away. So that is a typical slip casting process. We can end up having different kinds of geometries. Indeed, even the commodes or the the ceramic bases that we use in our washrooms are made by the slip casting technique. So what is that we did? So we have modified this slip casting technique just above the filter paper where we, which is actually in contact with the slurry. We have placed this micro patterned PDMS. Okay, so for instance, the PDMS is having this conical dimples, let's call, and then the ceramic suspension is placed on it. So you can add a sealant to help the demolding of your green body from the PDMS. So otherwise everything else is the same. So now how this is influencing our micro patterning, yeah, let's figure it out. So there are a couple of challenges during this drying process. Normally, the traditional slip casting would take maybe like 2, 3, 4 days for a drying process, because the water which is present in the suspension gets easily sucked out by the filter paper and by your plaster of Paris. While now we have added this PDMS membrane or a layer which is hydrophobic in character. So the static contact angle for a flat surface is somewhere in the range of 95 to 100 degrees. And if you are patterning it with positive protrusions, the the contact angle further increases and the hydrophobic behavior increases. So we also have seen that such kind of cases, it will it influences the drying of the slurry. So the second thing is that if we do a fast drying of this suspension with a PDMS micro pattern, we can have cracks that are formed in the specimens. And very interestingly, we even see this kind of depressions inside the specimens, like a macro depression. And that's when I started looking at the mechanisms more closely. So if we say that the blue one you see here is a slurry having alumina particles which are here in the white in color, and you have the structured PDMS. At time t equal to 0, we have it like, homogeneously dispersed slurry. And as after some time, the height of the slurry decreases because the water gets removed, and the mechanism of removal is both by evaporation as well as through PDMS. Yes, it's actually also through PDMS, and we will slowly see. And as we further go, we have experimentally seen that there is a clear water on the top of it, and a lot of sedimentation is happening here. And as we further go, you will actually see that on the top of it, it might appear very much solid, and we have tried to demold at this stage, thinking that it has completely dried out. But the interface of the slurry with the PDMS has been very much wet, and we have disintegrated the whole sample. So this is not, therefore the end of the drying is not here. We still had to wait for some more time until the full water at this stage has to be gone out by evaporation as well as by permeation through PDMS. Now, in order to try and quantify the drying process, so firstly, let us make a scheme and see what are all the mass transport phenomena occurring. So this is my colloidal suspension. So obviously the capillary transport, although it is indicated only in the vertical direction, it occurs in all the directions in the suspension, and there is an evaporation rate, typically, depending on the environmental relative humidities and also the enthalpy of vaporization of it. And then you have also permeation of water vapor, not the liquid water, because it's hydrophobic, it is not getting through PDMS. So the water vapor is permeating through this PDMS, and Wlet is called, for instance, the thickness of the PDMS. And we also have a lateral permeation into this another kind of PDMS, which is like very rigid and it is not so permeable to water. So this lateral permeation is so small, almost like 2-3%, that we kind of neglect the drying in the lateral direction, and we only consider the drying happening in the vertical direction. So we ended up having a one-dimensional linear model. So the drying occurs in the 2 stages. So for the first 24 hours, we kept the humidity at 90%, and the rest of the time it was 45% of relative humidity. So so we had used analytical expressions that are available from literature, and for the capillary transport, the Darcy's law is used, and where dP is the pressure gradient across the capillary length, and A is the cross-sectional area, and this is the viscosity factor, and this is the permeability. So all other how we can get this dP, and also the the hydraulic radius of the pores, those expressions are given here. So we need to understand whether the capillary transport mechanism is the rate determining process or not. So for that, there is an expression where you can plug in, and for the slurry heights of 17 millimeter, that is the maximum that we have used. So the capillary lengths are in the range of 8.5 millimeter. So from this we can conclude that it is not the rate determining process for majority of the drying, but if the slurry heights are like very big, so in that case it can be the rate determining process. So then we'll have to consider that in a series, and we'll have to get a net rate of reaction. So the evaporation can be modeled by Carrier's correlation equation, but given the uncertainty of the prediction, we have also experimentally investigated the evaporation rate, and the permeation of the water vapor through PDMS has been obtained by using the Fick's first law. So by using all these things, three equations and assuming that the capillary transport is not the rate determining process, the drying time can be given by this expression. Yeah, so just to see, the drying time is directly proportional to the slurry height. It's also directly proportional to the PDMS thickness, and you actually see that the base area of the pattern, so which is appearing in all three expressions, and it cancels out. So the drying time is indeed independent of the base area. So either you make a micro pattern area of 1 centimeter square or 1 meter square, it is actually going to be taking the same time. So in order to verify whether this analytical model is appropriate or not, we have conducted experiments. So we changed PDMS thicknesses from ranging 400 microns to 1.5 millimeters, and the drying time has shown a linear dependence. And for this kind of PDMS thicknesses, it's optimum because it's easy to handle. Of course, we can also do a spin coating, go to a lower PDMS thicknesses, and we can as well decrease the drying time. So that's why yeah, this is let's say one of the good finding of the work to use a smaller membrane thicknesses. And the second one is that for increase in the slurry height, so the drying time has also shown a linear dependence. So if you have, I mean, this is also valid only for until 17, 18 millimeter slurry heights. After that, as I already described, we need to look at mechanisms which maybe are having parallel or series series of transport phenomena. So the good thing here is that in literature people have manufactured ceramic tapes which are having thickness of 200 microns or maximum of 500 microns. By understanding the drying process, we have manufactured specimens as thick as 10 millimeters. So that's a bulk specimen. So one side of it is completely textured. Now it's independent of microstructured areas, and again in literature people have manufactured until 100 millimeters square, and we went on 300, 1200, and also 120 centimeter square areas. So given the fact that the master templates can be really huge ones, if you have such big furnaces in industries, for instance, we can make such very large area patternings which are very clean and which are very cost effective. So
Sriharita, sorry to interrupt. Okay, we'll have another 7 more minutes, so we'd like to leave some time for questions.
yeah,
So in a couple of minutes, if you can.
yeah, yeah. So yes, we can do sintering and try to look at the pore and grain morphologies. We can control depending on your applications. So these kind of patterns, for instance, you see can be used for the superhydrophobicity, and we have even used this ceramic as the master templates for further replication onto PDMS, and we have seen that the replication has been very precise. And you can also use them for tribology, like for instance dimples, because we know that if you have dimples, you actually decrease your friction coefficients. And you can also use it for diffractive optical elements where the depth precision is very good. So other features are Siemens star, these kind of wavy structures. And we have investigated also slippery properties. Normally alumina is omniphilic in character, but now when you impregnate the pores with a perfluoropolyether, you see that it is having the slippery properties. So similarly, we went on to study the friction properties, and we actually end up having very small friction coefficients for these lubricated impregnated materials. And the self-replenishment properties are also studied, and it has shown excellent self-replenishment. And so I'm not getting into the details, but if somebody is interested, they can look into this publication. So the key takeaways are that micro patterning on large areas is possible, and as I mentioned, it depends on the PDMS thickness and slurry heights, and we can really create huge areas. We made a knowledge transfer to Swiss watch company, and we are currently looking for collaborations in the laser patterning and also from the theory groups. So with this, I would like to conclude my talk, and thank you very much, and I'm happy to take questions.
Thank you so much. It was a very nice talk. We have time for some questions from the audience.
Kaushik, can I ask a few questions?
Yes, please go ahead.
Hey, Sriharita, this is Basa here. Very nice talk. I have two questions. One is you mentioned that in terms of the viscosity, you identified 25 8% alumina slurry as the optimum, right? I didn't understand in what sense was it optimum? Is it in terms of the uh, you know like say um, uh, I know the rheology is important for the processing, but was it difficult to pour it and make it into a thin film? I didn't understand the context in which you identified that to be an optimum. That's for question number one. And the second question is, you see the alumina particles that you use, they're really huge. I mean, millimeter size. You know, they settle, right? Density of these particles is close to about 4,000 kg per meter cube. This is alumina, Al2O3, right? So in that context, I mean, and also in one of the mechanism you talked about, 4 different times, and he said, initially, they start sedimenting. There is but looking at the sedimentation time, everything seems to occur very fast because of the density difference as well as the size. They would settle down very quickly. Again, in the same context, you mentioned that Al2O3 was stabilized by using PAA, one of the charged polymer, right? But the particles being so huge is really necessary because they would anyway settle, right? So these are my thoughts of the work. So
okay, yeah. Thank you, Basav. So the first question, the viscosity. So for that given recipe, we like, for instance, the major problem that was occurring is the deagglomeration by mechanically breaking. So if we had very high viscosity, we needed high energy milling. Of course, then the viscosity could be further high. It was just that for that particular equipments and recipe, that was the thing. And if we go to very small viscosity, then the sedimentation would be even more pronounced, and we end up having very thin films, thin specimens. So that's how the viscosity optimization was done. But lately I realized that, yeah, we can actually go for a very high energetic ball milling and break down those particles and have a, more like a semi-solid format. So that is possible too. So you're right with the question. So the second one, the particle diameters are in the range of 150 to 200 nanometers. They are not very huge. So the sedimentation times were not too small. So by calculations, for the whole slurry to sediment, it took almost 6 to 6.5 days. And also experimentally, I have observed that the slurry is not settling down too quickly. So it's in the matter of days. So like the third question, sorry, I forgot your third question.
I was under the impression that the particle sizes were really huge. So in that context, using a polymer for stabilization, I was wondering how effective it was. That was my question. But you mentioned that the particle sizes were nanometers, is what you mentioned?
Yeah, from 150 to 200 nanometers. So they're like ultra fine grains.
You had a distribution data, right?
Right. Yeah. So this
okay. Okay, yeah. Thanks so much.
Thank you.
Hey Kaushik, can I ask a question?
Yeah, sure. Go ahead.
So she had a very nice talk, very informative. So this, so the most time-consuming things might be your laser ablation also, right? Because you're talking about this 1 meter cross 1 meter sheet. So how long does it take for the laser ablation? And is it like, how scalable is that method?
Yeah, so I'm not a specialist in that, so I procured it, but I will try and answer as much as I know. So it takes like couple of days. So the full thing, like 3 meters square sheet, it takes like 2-3 days at a stretch, all 24 hours working. Scalable, if you have that whole system, if you can like you have that granite bottom counters, and if you can arrange all your lasers accordingly, it's possible. The only thing here is that it is a mask based projection system. That means we are getting the mask from the electron beam lithography. Once you get the mask, you can create really as huge as possible. So it's pretty much scalable. So
the mask also has to be that big.
No, the mask will be small, but then that will be like we create AutoCAD of it. So
Yeah.
so that the whatever dimension of the mask it is there, whenever we make it, like, you know, whenever we stitch them, we also make sure the stitching is very soft and it's not having a very strong interface. So that has been also extensively studied, and the X and Y stage movements are very precisely controllable, so that you can actually have very big specimens.
Okay, thank you. And this monodispersed particles, how are they formed? Is it forming some, like, how is it getting polished? Because in this particular slide, so there are a lot of agglomerated ones, and then you have looks like monodispersed particles. So how does it go from the step 2 to step 3?
Okay, so here the first thing is that we use an ultrasonic probe, then use it to actually break down these agglomerates, and we add an octanol because that acts as a surfactant, and that could actually decrease the interfacial tension between the, you know, air bubble. It's basically at the air bubble and the slurry interface, and we do a rolling for 48 hours. Rolling means we add alumina beads which are having 1 millimeter in diameter into the slurry, several of it, and then roll it for like 48 hours. So it's low energy milling.
Okay, thank you.
Thank you so much. There is a question in the Q&A box. Shri Harita, if you can just answer that in the meanwhile. We'll just move on to the next talk. So please join me in thanking Dr. Shri Harita Rautu for a very interesting talk. Our next speaker is Dr. Ratul Dasgupta. Ratul, are you here? Can you please
Are you
share
actually find?
Yes. Shall I share my screen?
Yes, please. Shri Harita, can you just type out the answer down in the Q&A box if you don't mind?
Sure. Yeah.
Thanks.
So much, and yeah.
Yeah, are you able to see my screen?
Yes. So our next speaker is Dr. Ratul Dasgupta from Department of Chemical Engineering, IIT Bombay. Go ahead, Ratul.
Yeah, thank you, Kaushik. So, so my name is Ratul, and I'm at the Department of Chemical Engineering at IIT Bombay. Is it okay if I don't switch on my video, because then it kind of interferes with my slides?
That's fine. Yeah, please, by all means.
So the work that I'm going to be talking about is jet formation from nonlinear capillary gravity waves today. And we started thinking about this problem about 4 years ago. This is my first PhD student with whom we started doing this problem. He has recently graduated, and now he's a postdoc. And the work that I'm going to describe today was mostly done by Shashwat along in collaboration with Palash. Shashwat is another PhD student who has joined 2 years back. And Lohit, who is a very recent PhD student, has also contributed to some part of this work. Now, in my group, basically this is the multi-phase flow group at the Chemical Engineering Department at IIT Bombay. We work on these two broad areas of research: waves on fluid interfaces and elastoplasticity in amorphous materials. Today's talk is going to be mostly on waves and fluid interfaces. And because this is a talk on waves, so I thought that I'll start with Lighthill. In the first talk by Shubhadeep, you have already seen a reference to Lighthill, and this is the second time we are bringing up Lighthill again. So James Lighthill was someone who thought deeply about waves. So this is a slide. I think he made this with his hand, and this was a presentation that he made way back in 1966, and where he listed down around 26 different kind of wave systems that can occur in fluids. Okay, so the shapes have some meaning and things like that. Now, in my group, we mostly focus on interfacial waves. So these are, I've also taken the liberty to modify this and bring in some more recent waves, waves which have attracted a lot of attention in the literature. One of them is Faraday waves and constraint capillary waves. So as I said, in my group, we look at mostly interfacial waves, and these are some of the kinds of waves that we look at in my research group. And today's talk is going to be on this, waves on deep water. So we are going to be looking at capillary gravity waves and deep water. Now this is a recap slide. So and this is a classical area of fluid mechanics. So if we have an interface which separates two immiscible fluids, let's say air and water. So this is what is indicated in white color here is the interface. So if you have air above and water below, for example, if you have a rectangular container and if you perturb the interface in the shape of a Fourier mode, which is like this, or if you have a cylindrical container and you perturb it in the shape of a Bessel function, which would be like this, then from a linearized analysis, from a linearized inviscid analysis, one can actually show that in a few steps of algebra, that the interface would move up and down harmonically in time, and the frequency of oscillation would be given by this dispersion relation. Now here K is the wave number, and G is gravity, T is surface tension, and rho is the density of the liquid below. Okay. So now this dispersion relation is a very well-known dispersion relation. It was first derived by Lord Kelvin almost 150 years ago, and we will come back to this dispersion relation again in this talk. Now, because this talk is going to be on waves jets in nonlinear capillary gravity waves, so I thought I'll start with a movie. So what I'm going to show is actually the collapse of a bubble. So what we have created here, this is a simulation which has been created using the open source code Basilisk. So what we have done here is we have air on top and water below, and we have created a cavity. The cavity is truncated, and so there is air inside this cavity. Now there's surface tension in this simulation, and so this is not an equilibrium configuration. So if you start the simulation, this is going to evolve in time, and you will see that the cavity actually collapses, and there will be waves spreading out radially outwards. This is an axisymmetric simulation, and you will see something interesting happening at the center of the cavity. So you can see the collapse happening. And as the cavity collapses, you will see that this jet is formed, which rises upwards and ejects droplets from its tip. Now, this jet forms not just in this kind of scenario where you have a bubble which bursts at the surface. It also happens in many other processes like Faraday waves. I'll talk about Faraday waves in my next slide. It also happens in cavitation, in the collapse of cavitation bubbles, in water entry of projectiles and things like that. And this is of interest both from a fundamental viewpoint as well as a practical application viewpoint. So for example, in oceanic sciences, in the open oceans, this kind of bubble bursting produces these jets on the surface of the ocean. And this is one of the leading causes of ejection of aerosol, the sea spray aerosols from the ocean, which plays an important role in formation of clouds. There are also other applications in drug delivery, particularly related to Faraday waves. Now, what I have on the left-hand side here is one of the first experimental visualizations of this bubble bursting phenomena. So this was in those times in 1954. This was, I think, one of the first high-speed visualization of this bubble bursting thing. And the precise details of how this jet is formed became clearer much later in the study by McIntyre in 1972. So this is actually a superposition of, again, a series of high-speed images taken at quick intervals. And what you actually see, so these are actually slices of the interface. So what you actually see here, one of the first one, which is one here, is actually the cavity, which is roughly spherical in nature. And then as time evolves, this sharp edge becomes a toroidal kind of a rim here and a rim here. This is almost nearly axisymmetric. And we also have about, so as time evolves, you can see that there are waves which are propagating and they get focused at the axis of symmetry. And there's something interesting happening in the interface, which is labeled 6. You can see that there's a small bulge which has appeared here. And as time evolves, this is the bulge which we'll call a dimple in my talk today. And you'll see that this dimple is basically the precursor to this jet, which eventually forms and ejects droplets from its tip. Now, I'll show you that this dimple is basically a nonlinear phenomena. You cannot really explain this from a linear theory. Now, in more recent times, it is also possible to simulate some of these things from by direct numerical simulations of the Navier-Stokes equation. This is a more recent study which has appeared in PRL and which has simulated this problem. And you can note that the qualitative features are the same. So this is an experimental study and this is a numerical simulation. Of course, the jet appears much sharper here due to the difference in the bubble sizes and so on. Okay, so coming to, as I said earlier, it is not just in bursting bubbles that these kind of jets appear. They also appear in what are known as Faraday waves. So what we have here on the left-hand side is a cylindrical container containing a mixture of water and glycerin. This is being oscillated vertically at 7.84 hertz and at a peak acceleration of about 3.23 meter per second square. Now, these numbers correspond to the figure on the left. They're slightly different for the figure on the right. Now, both the figures are actually not a single figure, but a superposition of many figures. Okay, so what actually happens is once you exceed a threshold of acceleration, one starts obtaining waves on the surface, and at every successive oscillation, these waves grow in amplitude. What is shown in the lower part of the figure is actually the trough part of the cycle. So the trough actually starts with being a near vertical thing, and then it kind of becomes this V-shaped structure. And then eventually it produces this jet which shoots upwards and at a very high speed and starts ejecting droplets. Now this is very similar to what we have seen earlier in bubble bursting. Now the same thing also happens here. This is a more viscous fluid. This is a slightly less viscous fluid. Now, coming to the theoretical understanding of this one, there has been a number of theoretical studies, both in the early part of the decade and as well as later parts. One of the most influential papers has been this, which appeared in 2000, and they have basically argued that the formation of this jet is preceded by a singularity. So you can understand that why this is a singularity. You can see that at this point where it roughly looks like a cone. The curvature is very large. So they argued that this jet is actually preceded by a singularity in the local curvature and the surface velocities. Okay, so there is a divergence in local curvature and surface velocities, and so very close to the singularity, it does not matter whether gravity is there or not, and the dominant balance is between nonlinear inertia and surface tension. Okay, so you can understand why the curvature is very large here, and so gravity, even if it were present, which it is in this case, would be negligible compared to the accelerations otherwise, okay, caused by the pressure gradient developed due to surface tension. And so they wrote down these equations. These are basically simple equations: Laplace equation, the kinematic boundary condition, and the Bernoulli equation, with this pressure jump term coming from surface tension. Now these equations were then scaled and written non-dimensionally, and a similarity ansatz was made. So these are all scale variables. So this is a non-dimensional h and non-dimensional t and a non-dimensional r. And a similarity ansatz allows one to write these things as power laws, and so this is some function of this argument. And then one can argue that if there is a similarity solution, then it would lead to these kind of exponents. Now one can also argue using the same similarity solution that very close to so t naught here is the time where the singularity happens, and very close to the time where the singularity happens, the argument of this would diverge. And so in order to keep h finite, so h is the interface here, so in order to keep h finite, this f would be a linear function of its argument. Okay, so you can see that that would basically imply that this you can see that beta is negative here, so this will be r divided by t naught minus t to the power 2/3, and if this is linear, then it just comes out, and so the t minus t naught to the power 2/3 and the 2/3 in the denominator cancel out, and it just becomes a function of r. Okay, which essentially says that it is a linear function of r. Okay, now you can see that this is true actually. This picture where you see a cone is actually taken very close to the singularity, the lower part of the picture, and you can see that this structure of the interface is actually reasonably a straight line around the singularity. Okay, so this study was very influential, and it kind of extracted some of the essential aspects of this singularity. Now, since then, there has been a number of studies subsequently into this problem, and there has been a lot of intense work continuing all the way to the present day. I'll not have time to go into the details of some of these studies, but I'll straight away come into how did we get interested in this problem. And for that, I'm going to show you a simulation. So this is a simulation of waves in a cylindrical container, and what we have is a free oscillation. So we perturb the interface in the form of a Bessel function. This is a single Bessel mode, which essentially means that I'm injecting energy into only one wave number initially, and this epsilon is a proxy for nonlinearity. So epsilon being sufficiently large essentially means that the amplitude of the wave has been chosen to be sufficiently large. And if you let the simulation proceed, so I'm just going to make this a little bit faster because this movie plays very slowly. So you will see that a very similar jet arises from the center, so, and it rises upwards and it starts ejecting droplets from its tip. Okay, so now this is how we started getting interested in this problem. So we had reported this in 2017, and it is very clear. So the basic question that we are now asking is, how does one understand this jet? Because we think that this jet is analogous to the jets that have been observed in Faraday waves as well as in the case of bursting bubbles. Now it's very clear that this is not a linear phenomena. The reason is because if, as I told you earlier, if you start perturbing the interface at time t equal to 0 as a single Bessel mode, one can show very easily from linear theory that from linear implicit theory that it would just go up and down in time harmonically, okay, with a frequency which is given by this dispersion relation that I showed you earlier. Now, you can see from here that this interface as a function of time would not give me any jet. This would just keep going up and down harmonically in time. Okay, so it would not produce any jet or anything like that. And so it's very clear that the shape of the interface, in order to capture the sharpening of the interface and the formation of a jet, we need some kind of a nonlinear theory. And so the task was to first establish that the jet that we are seeing in our simulations is very analogous to the jet that was seen in case of bubble bursting and other such phenomena. So for that, we looked very carefully at the simulations. So again, these are simulations done using the open source code Basilisk, and I'm going to show you a moderate value of epsilon, which I told you earlier is a proxy for the amplitude of the wave. This is actually a non-dimensional quantity, but you can think of this as the non-dimensional amplitude of the wave. So we have this Bessel function. This is all the interface is perturbed as a single Bessel function. So there's a single wave number here. And then as time progresses, you can see that it kind of moves down. So we start with a crest and then it becomes a trough. But on its way to becoming a trough, you can see some structure forming here in this yellow line. This is somewhere at around this time. Sorry, this is in this blue line, which is around this time. And then it forms a very smoothen trough. And then as this trough rises upwards, it again forms this bulge-like structure. Now, this is what we call a dimple. And later, when I compare with theory, I'll show you that this dimple is not captured by linear theory. This dimple is not predicted at all by a linear theory. And one needs some kind of a nonlinear mechanism to create such kind of dimples. Now you can see two things. One is when the crest is going downwards, there is already a dimple-like structure created. This dimple is kind of a broad structure. Its width is smaller than the original crest with which we started. But the next time this dimple is created, the horizontal extent is even shortened. Okay. Now, if you make epsilon even larger, then this phenomena kind of gets aggravated. Okay, so this is at a higher value of epsilon. So this is a even more larger amplitude wave. So we start with this blue line, which is time t equal to 0, which is a single Bessel mode. And as it goes down, so I have not plotted the curves as it goes down, but straight away plotted very close to just after it hits the trough. As it rises upwards, you can see that this dimple-like structure, and this is its width is much smaller than the width of the crest in the parent wave. And as it forms, as it goes up, it does something very interesting. The first thing it does is it starts rising higher than what it started with at time t equal to 0. So there's some kind of energy focusing going on at r equal to 0. And this is what we call as overshoot. Now, the same thing happens if you increase epsilon even further. And this is, again, a similar plot. And you can see that the overshoot becomes even more. And then you start getting droplet ejection at the tip. Okay, now I would like you to compare this phenomena with the one that I had showed you earlier. This is for a free oscillation problem. And this is where you have you deform the interface as a cavity. This is basically the bubble bursting experiment. And you can see the qualitatively similar features between these two problems. Okay, so the basic idea was that because here we are starting with a single Bessel function, this problem is theoretically more amenable to a nonlinear calculation rather than this problem. And so we wanted to understand how does jet formation happen here, with the hope that it will eventually help us to understand how does jet formation occur in these systems. So with that, we start our theoretical foray. So what we do here is we ask a question that how do we formulate a nonlinear theory? And here we want to use epsilon as a small parameter. A word of caution here that I have already showed you that the dimple-like structure already starts forming at around epsilon 0.5. So there is some hope of using epsilon as a perturbative parameter. However, we cannot really hope to use a perturbative theory all the way to epsilon greater than 1, because by definition, a perturbative expansion is valid only for epsilon less than 1. But as I'll show you, our expressions that we obtain by the perturbative expansion do not diverge even if you apply them at epsilon greater than 1. And so they kind of give us expressions whose validity we will compare later. So let's start with the strategy of how are we doing this. So what we are doing here is we start with the Laplace equation. These are the kinematic boundary condition. This is the Bernoulli equation with a pressure jump due to surface tension. Note that we have both gravity and surface tension because we don't want to assume that gravity is negligible to start with. And then this is just a mass conservation condition. And then we have some boundary conditions at the wall of the container as well as at the axis of symmetry. Now the strategy is to solve these equations perturbatively up to second order in epsilon. Okay, so first order is a linear theory. So for that we non-dimensionalize this. I'm not going to go, the calculation is a long one, but otherwise it is a straightforward calculation, and it's just algebraically very tedious. And so we non-dimensionalize this, and this leads us to two non-dimensional parameters. One is epsilon, which I introduced before, and another is like an ratio of surface tension to gravity. So this is like an inverse bond number. And we deal with order 1 bond number here, which means that we are essentially looking at ways where gravity and capillarity are roughly in balance. So we are looking at that kind of wavelengths. And then we expand all our quantities in powers of epsilon, okay, assuming that sigma is an order 1 quantity. Now, our detail here is that because we are doing we are expecting to do a nonlinear calculation, we also have to stretch time. So this is a detail. I'll not get into the details of this, but our main hope is that phi1 and eta1 will contain the linear aspects of the problem, and phi2 and eta2 would contain the first nonlinear corrections. And we are interested in the qualitative features of what is there inside this quantity, this function and that function. Okay, so this is what we are after. Now, the strategy is to substitute or to non-dimensionalize the equation, substitute all this, and derive PDEs for phi I and eta I. So phi I and eta I are basically phi 1, eta 1, phi 2, eta 2, and so on. Again, I'm going to skip the details, but once you have got equations for phi 1, eta 1, and phi 2, eta 2, one does an eigenfunction expansion. Here, this basically comes from the geometry of the problem. So we assume that this can be written, and this can be shown more rigorously, that this can be written as a infinite series in the Bessel modes and followed by a depth dependence, which is exponential. Each of these takes care of the Laplace equation, because each term in this series is a solution to the Laplace equation. We do a similar expansion for eta, the interface variable. And then our problem eventually becomes, because the spatial dependencies are all known, our problem eventually reduces to determining equations which cover this P and this A, which are functions of time. Okay, so eventually we get these ordinary differential equations. And this is in some sense a simplification, because we started with this complicated nonlinear set of PDEs to start with. And what we have reduced this is to a set of linear ordinary differential equations, which are reasonably easy to solve. Okay, so we can solve these things analytically. And I'll just point out the qualitative features of the linear solution. So phi 1 and eta 1 are the linear solutions. There's nothing very interesting in them. They just predict that if you inject all your energy into one mode, it just goes up and down in time harmonically and with some frequency which is known. Now, the first nonlinear correction, which is given by phi 2 and eta 2, is more interesting. So it predicts something very interesting. So I will just focus on eta 2, which is the correction to the interface. It says that at the second order, the energy which we had injected into only one mode kind of gets distributed in the entire spectrum. So if you recall that we had done an expansion and then there were infinite number of terms, and at time t equal to 0, I had put all my energy into just one term in this expansion. So the nonlinear correction actually tells me that there is this energy kind of gets redistributed into the entire spectrum. So this entire spectrum is excited at second order. So that is what is the nonlinear effect. And if we just compare this with simulations, so what I have here is a bunch of figures for different values of epsilon. And what we are doing is we are looking at the interface at the axis of symmetry, which is r equal to 0, and we are tracking it as a function of time. So this is the interface, and this is a time in all of these pictures. So you can see that for small epsilon is just a harmonic function. There's nothing much going on. But as epsilon becomes larger and your dimple starts appearing, you can see that this is the interface. You can see that the nonlinear theory is able to capture this dimple formation. The linear one in yellow is not. And you can see that the time signal also starts deviating. The nonlinear theory and the simulation are kind of together. The linear theory starts deviating. As we go to higher values of epsilon, you see even more deviations. And you can see that the early dimple is captured by the nonlinear theory, but the later dimple, which comes when the trough is rising upwards, is not kind of well resolved. And I'll get into this towards the end of my talk. Now, this is...
Yes. Sorry to interrupt. We have another maybe 6 to 7 minutes, so we'd like to leave some time for questions.
Yeah, so I'll just finish here. So we have compared, so these are all comparisons. So, I mean, I've kind of told you the gist of this. And as I told you, the theory can resolve the precursor dimple which forms, but not the later dimple. And it can kind of also resolve the overshoot and things like that. And I will just spend a few seconds in just telling you why the first dimple is resolved, but the second time the dimple appears, it is not resolved. So this is the first dimple, you can see it is resolved, and the second dimple is not resolved. So you can think of the vertical axis as a Fourier transform, and we are kind of measuring at this instant of time what is happening. And as I told you, the energy is getting distributed across modes. So you can see that in the simulation, we have kind of, these are the modes, and we injected all our energy into mode 5 at time t equal to 0. And you can see that at a later time, many of the other modes have got excited. Okay. Now, but this spectrum is kind of captured well by the nonlinear theory up to this time. Okay. So in particular, there is significant amount of energy in mode 10, and the theory kind of captures that well. Now the next time the dimple forms, this is a shorter dimple, and what actually happens is even higher modes start getting substantial amount of energy, and because this is a second order correction, the second order theory cannot capture the energy in the third mode very accurately, which is the reason why it is not able to capture. So this is overall a nonlinear phenomena, and basically what actually happens is the energy gets spread into the spectrum, and the order of the theory basically tells you how far you can go into the spectrum. So with this, I'll stop here. So we have formulated a nonlinear theory which can resolve the inception of dimple formation, and the nonlinear theory kind of also tells you in time that how does the energy transfer happen from starting from capillary gravity waves at large scales to pure capillary waves. So this is one slide which I did not show, but here you can actually see that very close to the onset of dimple formation, it's purely a capillary event, and gravity really plays no role because the accelerations are much larger than gravity. Okay, so I will stop here and I'll just switch on my camera.
Thank you so much, Ratul. That was a very nice talk. We have time for some questions. If it's okay, maybe I'll start with one. Maybe this is a slightly naive question, but usually if you have a dispersive PD and you put energy into a Fourier mode,
yes,
the dispersion relation is sufficient to make sure that the energy is dispersed, right? But here you have a non-trivial dispersion relationship, but still everything is in the J0 K1
yeah.
single K. Right?
Yeah. So
why does that happen?
So the main reason is because although your medium is dispersive, but we are not injecting energy into the full spectrum. Okay, so it's really a matter of initial conditions. So although your medium is dispersive, but if you have a linear mechanism, if you don't allow for non-linearities in your equations, and if you inject all your energies into one mode, even though your medium is dispersive, but you did not inject energy into all the other modes. So there is no mechanism of energy transfer across modes because a linear theory does not allow for a linear set of equations don't allow for energy transfer across modes. Okay? That's really a function of initial conditions. If you had a spectrum of modes which you had excited at time t equal to 0, then there would be, even then each mode would conserve its energy. But here we are injecting all our energy into just one mode.
I see. Okay, and the simulations where you showed the breakup right at the end,
yeah.
How do you keep track of this? Is it like a VOF method or something?
It is a VOF.
I see. Okay. All right. Other questions from the audience? Alok, you're unmuted.
Yeah, this is Gaurav. Alok is. I thought I'll ask a question. Then I was wondering if you should just call Ratul if you have to save time.
No, that's fine. Go ahead. We have time. Go ahead.
Yeah. So Ratul, your simulations would have some dissipation, right? So how does the dissipation affect the?
Yeah, so we have measured the dissipation. So typically so the numerical dissipation is, I think, what you are talking about. So typically within the first oscillation, the numerical dissipation is not large. The numerical dissipation starts showing up only in the second oscillation, and because the jet kind of arises within the first oscillation, so we start with a crest and then it goes down, forms a trough, and then next time it comes up as a jet. Okay, so the jet happens within the first oscillation. Okay, so we don't have to worry too much about numerical dissipation, but beyond that, yes, beyond that, we do need to worry about numerical dissipation in the simulation.
And the size of the container?
The size of the container is something which is contained in the theory. Okay, so the theory actually, so as I showed you, the theory actually models a finite container, so that's contained in the theory.
Okay.
The initial condition takes care
of that. You always get these oscillatory solutions. High frequency oscillations at the interface is what you get.
Yes.
I see. There is a mean displacement that you get over which you have oscillations, or?
Yes. So in the second order, you get that. So in the first order, in the linear thing, you will not have any change. So the mean level is, let's say, 0. And then in the linear thing, you will not get any change in the mean, but in the second order, you will get a change in the mean also.
So because of that is when you get this Worthington jet, or that's what you're saying, or?
Yeah, so I'm not sure I can attribute it just because of that, because that is just one term in the expansion, and I think there are other terms also. So there will be some contribution from there, but I am not sure we can say that it's entirely because of that.
Right. Okay. I'll give you a call.
Yeah, sure.
if you have time for one quick question,
Yeah.
again from the audience. Just a small clarification. You showed that the comparison between the theory and the numerics, right, at the end, which was able to capture those. Is it just a matter of adding more terms in that expansion, taking more higher order terms to?
Yeah, it is indeed a matter of adding more terms, but it quickly gets out of hand, because even going up to second order has been a pain. I mean, the algebra really goes up to, tens and 20 pages of algebra just going up to second order. So although it's, it is in fact a matter of going up to higher orders, but it's easier said than done. And then there are mathematical difficulties one runs into when you take into account both gravity and surface tensions, right? There are singularities that occurs in these equations at particular values of bond number. So I didn't have time to speak about that.
I see.
But there are issues if you go into higher order and things like that.
I see. Okay. Very nice. Thank you so much, Ratul, for a wonderful talk.
Yeah.
We'll
organizers once again for this opportunity. Yeah.
Sure. Thanks. So we'll move on to our next speaker, Dr. Vijay Krishnamurthy. Vijay, are you here? Yes, you're here. Okay.
Yeah.
So our next speaker is Vijay Krishnamurthy. You can see his affiliation on the screen. So please get started.
All right. Okay. Thank you. Thanks, everyone. Thank you for the organizers to give me this opportunity to present. So I'm at ICTS. I'll speak about single files and noise control in active particles. I also said I'll speak about anisotropic particles, but I realized I won't be able to do that in that limited time. So we've had several talks which sort of gave an introduction to active matter. So active matter is basically a novel class of non-equilibrium statistical mechanical systems. The basic idea is that they are driven at the level of the individual units, unlike a typical non-equilibrium system where you either heat the system, drive the system, or slosh it from the boundaries. This makes it a novel class. So typical examples are in the living world. Cytoskeleton of cells is a classic example of active materials, but there are also imitations like the driven granular materials on a shaken plate. Probably the more important thing to understand a condensed matter description or a statistical mechanical description of active matter somehow started by looking at hydrodynamic theories. So these are theories which are really valid at large length scales and long time scales. And so one looks at, for instance, the density field or the polarity field. So for instance, in this flock of starlings that you're looking at, each starling could be thought of as like a vector, a polar vector. And you write down a hydrodynamic theory describing these kinds of. So these are things that people have done. So classically, these represents generalizations of Navier-Stokes equations to these kind of materials. So P, the polarity field, is at the same time order parameter, which locally tells you how aligned the birds are. But it's also a velocity field because it also tells you that locally the birds get advected along the same velocity field. Now, the essential feature is not really about the orientation field. It's not really about the fact that these are objects which are asymmetric, which are not isotropic. But the essential feature is really that they break detail balance, which means they actually consume and dissipate energy at the level of the individual units. So there's been a lot of effort recently to think about minimal models for active matter, for active particles, without worrying about these complicated orientational effects and all. So one can really fish out the essential statistical and condensed matter physics approaches. So this is what's called scalar active matter. So the idea being that you have particles which are isotropic, so which means they don't have any orientational degrees of freedom. And so you declare by hand that there is some propulsion mechanism, some active force, which gives it an active velocity. And so you ask what are the kind of dynamics such particles can in fact exhibit. So one writes down overdamped dynamics, so which means the particle position, the rate of change of the particle position is given by an active velocity term. Some interactions could be with the wall or with the other particles, but they're isotropic in the sense that they don't depend on the local direction of propulsion of the active particle, and translational noise. Now, typically, there have been three models that people thought about when thinking about these kinds of active particles. So one is called the run and tumble particles. So these are particles which are sort of inspired by the motion of bacteria, E. coli in particular. So the idea here is that you write down an active velocity dynamics with a constant speed V naught, but then the direction of the velocity does a tumble. So every now and then with a Poisson rate gamma, the direction E cap suddenly flips sign. flips direction. So uniformly in 2D or 3D, and in 1D just flips sign in the plus minus directions. The other model is what's called active Brownian particle. And here you again say the active speed is a constant, but the direction does rotational diffusion. So for instance, in 2D, the E cap, which represents the local orientation of propulsion direction, does rotational diffusion. The third model, which has been quite useful to understand analytical calculations, is what's called the active Ornstein-Uhlenbeck process. So here too, you have an active velocity, but the active velocity does what's called the Ornstein-Uhlenbeck process, which means the active velocity, even though driven by, let's say, a white noise, this velocity will have a non-zero time correlation. And so it has a memory. It's like a colored noise. So this active velocity then feeds back into the evolution equation. So some features are that, so the first two models have constant active speed. The last two models have an active velocity which varies continuously with time. But the real key essential feature is that the characteristics of the noise, the active noise that you're putting, is the thing that distinguishes the three models here. But these are funny models in the sense that even trying to work out if you have a bunch of free particles, free active particles, like a classical diffusion problem that we do, you put them all at one point at the origin and see how the diffusion equation tells you the spread, the Gaussian spread that we typically think about. So if you try to work them out for RTPs in one dimension, turns out there are some very peculiar features. So for example, you don't get a simple multimodal, a unimodal distribution for all times. So sometimes at early times, it really becomes multimodal, and then eventually at very long times, you get the diffusion kernel. You can also look at very funny things appearing in simple systems with, let's say, even a harmonic confinement. So we worked out the case of a active Brownian particle, sitting in a harmonic confinement, isotropic harmonic confinement. Even here, the competition between confinement and activity sort of gives you very nice phases, sort of quote unquote phases, in the sense that where the probability distribution could be either peaked at the center of the trap or could be peaked away from the center of the trap. And there's some nice transition that happens between them. Once you put in interactions between particles, it turns out that they display some very nice and very non-trivial behavior. So for instance, this is an example of what is called motility-induced phase separation. So you have a bunch of active particles interacting with each other via completely repulsive and isotropic forces. Yet, when you put a large number of them together, you see signatures of phase transition happening. So this turns out to be a genuine phase transition in 2D. There is actually a large system spanning cluster of particles that will survive at long times. So this is motility induced. So to emphasize, no attractive forces but in the potentials, isotropic forces, yet motility, the active velocity, can actually make them phase separate. Okay, so with this, I want to turn to one of the stories that I want to present, which is trying to understand sort of scaling in active single file dynamics. So we want to understand emergent statistical mechanical properties of active particles, interacting active particles. Doing any analytical theory becomes harder in higher dimensions, so we turn to one-dimensional system. So the idea is simple. We put a bunch of particles, active particles, in one dimension. So it's a single file, so the particles cannot overtake each other. And let's say we do periodic boundary conditions. The boundary conditions don't matter so much. So we look at the equations of motion. So some typical particle has its x coordinate evolving according to this equation, where you have an active velocity, the forces coming from the neighboring particles, and some translational diffusion. So for simple RTPs, now the RTP active noise would be something that flips between plus and minus 1 at a Poisson rate. For an ABP, it would be something where VA times cosine theta, and theta does rotational diffusion. For an AOUP, the equation remains identical. So this system of equations, if you forget the interactions, if you just take free particles, so it turns out that mean square displacement is actually a nice scaled function of the parameters. So you can actually identify all three models by a simple mapping. And the mean square displacement turns out to be the same exact expression for all three models. So we wondered, whether this scaling will also survive when you put in interactions between the particles. So what we do is to take in n particles in a box of size L, and so therefore the density rho, which is n by L, number density, and ask that if you put in these particles with isotropic interactions, purely repulsive isotropic interaction, are there some very nice scaling features that come out there. So keep note of these parameters, U, omega, and rho. These are the things that I'll keep using regularly. All right. We will neglect translational diffusion for most of the stories that I'll show you today, because the translational diffusion doesn't seem to do anything we have solved the problem. Even with translational diffusion, nothing qualitatively new comes up. The first thing to notice when we do simulations of these particles is that they actually form clusters. That's nice. So what you're plotting is the trajectories of the particles in time, starting from some initial conditions. So first you see that the particles actually form very nice large clusters. They clump together. So this is reminiscent of the motility-induced phase separation picture. So why do they clump? I mean, the idea is that they clump when the particles can collide much before they can flip. So in the RTP case, if you flip much more before you collide, you'll essentially become like a Brownian particle. But if you collide much before you actually flip, you can actually aggregate. That's the basic idea. So it's simple. It's very similar to the MIPS idea that I showed you in 2D. But in 1D, there's a distinct difference that you can never get a single large cluster. So ABPs and AOUPs also show the same clustering behavior. The clusters are motile. So you see that when a cluster forms, the cluster moves as a whole. So for instance, something here, the cluster is moving as a whole and move. So that's amazing. I mean, so it's not like a lattice picture where the particles actually form clusters, but the clusters are stationary, but the clusters are motile here. So why does a cluster move? So it's very easy to work out that if you look at an n particle cluster, and if the n particle cluster has it such that its center of mass velocity is non-zero, surely it'll move. But then why does the center of mass velocity be non-zero? I mean, it turns out it's basically an imbalance of active forces. So think of the three-particle cluster. So this is a stable cluster. So when three particles come up in this configuration, all move to the right. It's a stable cluster. The cluster will not disintegrate, but they will all move to the right with the same velocity of an individual particle. On the other hand, if one of the particles has an opposite orientation, just keep this picture in mind, you will see that these two particles will cancel out the active forces, but this has a non-zero net active force. So this cluster as a whole will move to the right, but with a reduced velocity. The clusters are also not stable for all times. So in the sense, the clusters, as you can see from the image here, the clusters form, they disintegrate, form, they disintegrate. So why are they dynamic? Again, a simple picture can tell you the story. So it turns out that the center of mass velocity of the clusters itself is therefore a random variable. So how do we understand this? So let's say we have this stable cluster of 4 particles. And up to some time t, there's no flipping event. There's no change in the active velocity. So therefore, the cluster remains, first of all, stationary and stable. At some time t, one of the particles flips its direction. Notice this and that. So it flips its direction. Now, from this point onward, this entire 4-particle cluster is stable, but has a non-zero average center of mass velocity pointing towards the right. So therefore, this cluster as a whole will move. On the other hand, the same 4-particle cluster, if it turned out that one of the edge particles flipped the direction, flipped its sign of motion, well, this will actually break up. So you will see that this particle
Hello?
Yeah, looks like the presentation has stopped.
Yeah, I think Vijay has probably been disconnected. Can one of you just call him? Gaurav, Alok or Kushal?
Yeah, just 1 second. 1 second.
Yeah, looks like he's back.
Yeah, he's back now.
Vijay, can you hear us?
Yes, yes. I don't know why Zoom just logged me out suddenly.
Okay.
It was fine. I have no idea what happened. Am I back? Can you see me?
Yes, yes.
All right.
Yeah, go ahead.
Okay. So it turns out that if you look at the clusters, we wanted to ask if there is some nice statistical scaling properties and so on. So we found out that the average size of the clusters is actually a function of just this combination: the density, the active speed, and the persistence rate, the flipping rate, for instance. So that's true for all the three models, the RTPs, ABPs, and AOUP. So we kept one of the parameters fixed, two parameters fixed, and varied the variation of the active the average cluster size, and we found this relation in an empirical fashion. All right, so now we would like to ask what's the distribution of the cluster sizes, and it turns out that the distribution of cluster sizes actually showed a very nice scaling conjecture. So we found out that this distribution really satisfies a very nice scaling form, and that seems to work across parameters and across models. Not only that, it turns out that the dynamics of the particles, not just the static distribution of cluster sizes, but even the dynamics of the particles show some very interesting scaling behavior. It turns out that in single file, the particles actually slow down at long times and gives you a root T. So we did a heuristic theory, and it turns out that this heuristic theory is actually able to predict a very nice scaling form for the mean square displacement of tag particles, and that seems to be scaling even across parameters and models. So that's the summary of the first part. So what we found is that there is some nice universal scaling of the cluster size distribution and mean square displacement across models and parameters. And there seems to be a single parameter that seems to be controlling this. Not everything scales. So for instance, the cluster velocity distribution is very different for the three particles models. So it's interesting that there are things that don't actually agree with each other, but there are things which actually show very nice universal scaling. So let me come back to the scalar active matter problem. So I said these three models, and so therefore I said the essential distinction is really the characteristics of the active noise. And so we just showed that even with these three different characteristics of active noise, there is some sort of a universal scaling that's present. So we wondered, I mean, can we actually control this active noise and so therefore induce a transition from one kind of active particle to another kind of active particle? So this is work being done with Shashi Thutubali's group in NCBS. So what we're doing is an experimental study where we take a bunch of active particles and put them on a granular shaker. So this is our setup. So there's a granular shaker, there's a head, and you have a camera through which we can record. So the head has a 2D large arena in which the particles can move around freely, but also has channels. We'll come to the channels in a minute. So what we do is to engineer our 3D active particles by just 3D printing them. And the particles have a slight asymmetry in their shape, very slight. And this actually makes them self-propelled. So this is a well-known system which has been studied from the past 10 years to show that these are actually active particles. So we can actually look at the particles and just watch one of the movies, and you see a very nice persistent random walk for these active particles. So we can actually do image analysis, capture videos, do some machine learning algorithms, can actually figure out the positions of the particles and also the orientation vector. Remember, the particle is isotropic, but still it has a net propulsion direction. We can figure out the direction of propulsion. So it turns out that these particles are actually chiral. No matter what we did, we always ended up with chiral active particles. So fine, so that's a feature. Rather than a bug, we made it a feature. So it turns out that the particles can actually be described very nicely by an active Brownian particle model with just the addition of a new chiral term. We can calculate the mean square displacements for this model analytically. And it turns out that we can actually fit the solution, the experimental data that we get for the mean square displacement with our theory. And so therefore figure out all the parameters in 2D. So we have the chirality, the translational diffusion, the active speed, and the rotational diffusion. We can control all these things as a function of the amplitude of shaking of the relative to gravity, for instance. So here comes the funny thing now. So we said noise control. So this is an active Brownian particle model. Can we actually control the noise? And the answer we found is that yes, it can. And the answer is confinement. So remember, I showed you these grooves. So what we did was to now put the particles in these tiny 1D channels, quasi 1D channels. And so you look at the geometry, the width of the channel is some parameter W, the particle size is some D. And so it's really the ratio of the particle size to the channel width that matters. To set up the geometry, the polar angle is theta and the relative angle is phi. So when you actually have a channel which is wider than the particle diameter, so the particle can freely move, you actually see the motion of the particle, and it looks like an ABP, which is more or less confined inside a channel. So you see the relative coordinate psi and the theta coordinate, that position coordinate, and the position coordinate is just doing translational diffusion. Something very interesting happened when we confined it to a channel which was comparable to the particle size. So we had a channel width which was comparable to the particle width itself. And now if you actually look at the motion, you find that the theta coordinate just goes straight in one direction, randomly flips a direction, flips its direction of velocity, and goes straight again. And so what you see is some sort of a run and tumble motion that's coming up. And in fact, if you look at the dynamics of the psi variable, this looks almost like a molecular motor doing stepping, walking in the problem. So there's run and tumble particle for the run and tumble motion for the translational coordinate, and a motor-like dynamics for the internal coordinate. So this is the picture, this is a trajectory. So you see the psi variable really showing you a motor-like dynamics. So one state, another state, one state, another state. And so these are the flips that are happening. So whenever it's in one of the states, the translation coordinate just moves almost rectilinearly. So there is some tumbling time. So it's a runtime tau. And after these runs for a time tau, it does a tumble. It flips its direction of motion. So the probability distribution of these run times is actually turns out to be a double exponential. So this is a functional form that we fit, and we'll come to this later on. So it seems that there are two time scales for the problem. And so the two time scales, the KF, the forward and the backward flipping rates, are the thing that's controlling this tumbling motion. So this emergent tumbling motion, how do we understand that? Well, if you write down the simple kinematic equations in 2D and specialize them to the 1D case with a constant radius, turns out the equation for the theta coordinate is just some simple thing, where the parameters nu and the script d and all, these are all things that we have figured out in 2D. But there's no guarantee that the 2D parameters should remain the same when you put them in confinement. To check that, we actually computed the correlation function of the active noise. So this will therefore be the active noise in the run and tumble particle, which is characterized by the variable theta. And so we can actually predict a correlation of the theta, the mean square displacement of the theta, with the correlation of the sin psi active noise. And in fact, the theory and the experiment actually match very well. So we're using the 2D measured parameters. We measured this experimentally, we measured this experimentally, and they lie on top, provided we know these parameters. And these are the parameters that we used in 2D. So therefore, the parameters inferred in 2D are valid in the quasi-table. So, but how do we understand them? Remember, the particle interacts very strongly with the walls. I mean, it's complicated. There's friction, there's roughness, the shape of the particle matters, and probably also the shaking amplitude matters. Now, trying to model the particle wall interaction is going to be a very hard job. So we got a cue by looking at how the internal coordinate psi looks like. So it turns out that the internal coordinate has a double peak distribution, and the two peaks are somewhere near plus minus pi by 2. So we wondered, I mean, can we just get away by modeling the particle channel interactions by simple periodic force? So for instance, in the equation of motion for the internal coordinate, rather than just having chirality and some kinematic term that automatically comes up and translational diffusion, we put in an additional noise, we put in an additional force. So this is something that's trying to capture our confinement effects. Whether this works, we don't know. So it turned out that it does work. So for this problem, we can actually solve this exactly. We can find out the Fokker-Planck equation, solve the system. And this is a classic thing which is known from the past 25 years. This is basically the Brownian ratchet model of molecular motors. So immediately the connection becomes nice. It was really like a motor. And lo and behold, this equation does capture the motion of a Brownian ratchet model, periodic potential, periodic tilting potential. And there is an exact analytical solution for the probability distribution. And so if we compare the data, we only have one fitting parameter, which is basically the strength of the potential. All of the parameters measured in 2D, and the data and the theory match very, very well. So this is a very nice picture that tells us that we understand this. One last thing, we can also predict the two transition rates, the forward rate and the backward rate. So because this is a tilted potential, going from here to here and coming from here to here are not the same. But you can use Kramer's theory for this potential and ask whether your simulations and experiments will match with the theory. And it turns out it's reasonably good. I mean, so if you look at the ratio of the forward to backward rates and study that as a function of chirality, here's the theory prediction from Kramer's, and these are the experimental data points. So it also matches very well with the numerical simulations. So I'll summarize that. So we found there was a granular active particle, and it showed nice emergent dynamics in 2D, like an active Brownian particle. And we confined it, and the confinement actually led to an emergent RTP-like dynamics. So what we have demonstrated now is that lateral confinement will actually make an ABP particle and turn it into an RTP-like particle. So this sort of opens up a very nice set of things. So if you want to study across models and all, you can really tune this. So let me thank my collaborators for the 2 stories and the funding sources. So if there are questions, that'll be very nice.
Thank you so much, Vijay. It's a very nice talk. We have some time for questions from the audience.
Kaushik?
Yes. Yeah, go ahead, Ravi. Yeah, go ahead.
Vijay, it's a very nice talk. So here you are seeing this second evolution, square root t. So is it a kind of subdiffusion, or how do we understand it?
Exactly. So this is a standard thing which is known even for simple diffusing particles. If you have Brownian motion, but you confine the Brownian particles in a 1D channel, then it turns out that the initial mean square displacement will be like t, which is the simple diffusion. But once the particles start interacting with each other, bumping into each other, that will slow them down. And you can show analytically that the long-time diffusion coefficient, long-time mean square displacement really goes like root t. So this is known even for simple Brownian particles. For our active particles, it turns out that we have a crossover from a t-square behavior, the initial time, ballistic, to a root t behavior. We didn't see much of a t behavior, also because we didn't have translational diffusion.
So in this case, clusters, do they matter?
Yeah, exactly. That is the nice thing that we have found. The clusters are there even at the root t time scale. So that is the whole point that we are trying to understand. That even though you're looking at subdiffusive motion, it's in some sense the subdiffusive motion of the clusters themselves. The clusters have become the superactive particles. And it's really the subdiffusive motion of these superactive particles in a single file, which is really giving you this root t behavior at long times.
And one more, what is the effect of anisotropy of the particle in such systems? We are working on rod-like systems, active rods.
In experimentally? Oh, no, I didn't know. The first part of the experiment. So experimentally, people have studied a lot. For example, one of the first things that I showed you was really looking at active. So for example, this movie, right? So this is really looking at rods, polar particles, but they have a bead of, they have a bunch of beads, and the beads form like an elastic bath. And if you have polar particles or a rod like, so there's also the orientational effects that come in. And in the interactions between the particles will no longer be isotropic. So it becomes more complicated. So you have to worry about not only the position of the particle, but also the orientation of the particle. So in the case of the scalar active particle, the orientation only serves to define the direction of motion. The interaction between particles is isotropic, much, much simpler. You can understand things much, much easier.
Yeah, thank you. Thank you very much.
Hey, Bijay, this is Tarak here. So this hi, I'm Tarak from IIT Madras. So this root 2 things is because you don't have enough time scale, you have not run it longer, or is it because the nature of the systems, even if you run long, it will still remain root T?
It will remain root T. So like I said, even for simple Brownian particles, it remains root T at long times. It's essentially because the idea is that the particles have become so crowded enough at long times that so it's really a competition between 2 time scales, right? So there's a time scale for diffusing a certain length, and there's a time scale and there's a length scale, which is basically the interparticle distance. And so on longer time scale, this motion, because it's essentially in 1D, the particles cannot overtake each other. They're confined because of the channel. And so therefore, this really slows down the motion. In 2D, it will never happen. In 2D, you can just go around the other particle, and that will give you T behavior at long times.
So in some sense, the particle never relax. I mean, it's never.
It has reached a steady state. This is people have seen experimentally as well. If you have colloidal particles in a 1D tube, for instance, I mean, basically the tube should not be large enough that particles can overtake each other. And this actually comes up. Experimentally, also people have seen this.
I see. Okay. Thank you.
Do we have time for one more question?
Yeah, sure. Danny, go ahead.
Hi, Vijay. Very interesting talk. So I have a question regarding your active particles that you showed in the end. So they are capable of 2D motion, right, in your experiments.
Correct.
Now, when you
Correct.
put them in a 1D, do you see time instance when, so now when you constrain them in 1D, do you see time instance when the force is oriented along the perpendicular direction, that is perpendicular to the wall, not tangential, and hence do you see them stop for periods?
Oh yeah. So because the particles can turn freely. I mean, it's not so constrained that the particles. Remember, the particles are more or less circular disks, and the diameter of the channel, the width of the channel is almost the same as the particle diameter, but slightly bigger. If it's too small, then it won't move. So the particles can freely rotate in the plane. So whenever their direction of propulsion is towards the wall, they get stuck. They don't move. So it's only when their direction of motion is along the tangent to the channel that they can.
But is that something you consider in your model? I mean, or is that something?
No. So that's what. So we didn't worry about all that. So I mean, initially when we thought about these things, we thought that all those things must matter. So we asked if we can just get away with putting in a simple potential, which is just along the channel, preferred direction of motion along the two directions of the channel. Is that enough to qualitatively capture things? It turned out it can capture even quantitatively.
Wow, excellent. Very nice. Thanks.
Okay, thank you so much. Thank you, Vijay, for a wonderful talk. Please stick around. There are, I think, a couple of questions in the Q&A box, so if you can answer them while we move to our next speaker, that will be really helpful. So our next speaker, the final talk for this session is by Dr. Divya Nair. Are you here?
Yeah, hi, Kaushik, I'm here.
Yeah, hi. Yeah, Divya, can you just share your screen?
Sure. So I hope you are able to see the screen.
Yes, yeah. So please go ahead.
Good morning, everyone. Welcome to my talk. First of all, I would like to thank the organizers of SMYM for giving me this opportunity to deliver this talk and discuss with you all some of the work that we have just initiated in our group. And today I'm going to be discussing this work, which actually I have done on my own because I did not have any PhD student when I began this work. So I just thought of starting something. And we have been now interested in understanding the macromolecular crowding effects as they occur in living cells and how they actually affect the self-assembly processes in biological systems, as well as how we can actually use these ideas once we understand them fundamentally to design self-assembled nanomaterials. So this is what the theme of our work is, and we mainly use molecular simulations. And today I'm going to present some of that work. So here I have shown a picture of a beaker with some blocks which are self-assembled in a very organized manner. And this actually is a very nice example of what macromolecular crowding effects are, where self-assemblies happen in a very crowded environment of some large-sized particles. So what a living cell looks like. A living cell can be considered as a very highly complicated system, which is in which there are large sized molecules, macromolecules, organelles present in a very confined space. So the typical cell size of the cell, as we already had a lot of talks on living cells and active matter, the typical size is of around microns, 100 micrometers, and we know that a lot of important biological processes occur in living cells. So here on the left side is a cartoon picture of a living cell, which is showing the number of atoms and molecules present inside the environment of a living cell. So we have large-sized ribosomes, which are the machinery that produce proteins. Then we also have the cytoplasm, which is like the crowded soup, you can consider like that, which has not only proteins, it has other macromolecules like sugars, lipids, fats. Then there are small molecules like co-solutes, what we call, like urea, TMAO, and alcohol, which play an important role in maintaining the different concentration of the other species inside the cell. Then we also have water, which we know which forms the largest part of the component of a living cell. But what is peculiar about water inside the living cell is that it's not as free as what you would expect in a dilute solution. So the point is that given the fact the cell looks so crowded, how do these biological processes occur? We know that a lot of processes that involve compaction of biomolecules happen inside a living cell. For example, protein folding, unfolding happens. Protein takes its native form, which is highly ordered structure in which it functions. Then DNA condenses inside the nucleus, which is again a very confined volume with a lot of other polymers and other species present around it. Then a lot of other reactions which involve diffusivity and movement of molecules inside the cell happen, like protein ligand binding, enzymatic reactions, transport across the membrane. So we do not completely understand that how the crowding environment actually affects these processes. So you can imagine a living cell to be like a crowded swimming pool where there are a lot of people packed in a given volume. So what would happen in a crowded swimming pool? There'll be a lot of people interacting with each other. Then the space or the volume occupied by one person cannot be accessed by another person. So these are called volume exclusion effects. Then the water is not free, as I said, so people are also not free to move around. So given these facts, it is expected that if these are the effects observed inside the living cell, they will affect the biological processes in some way. So we are interested to understand how these effects actually control or influence the self-assembly of macromolecules. So macromolecular crowding is not something new. It has been known for years, since 1950s, but these effects have remained underappreciated because of the limitations of studying these systems. Experiments, it's very difficult to experimentally study these systems, as I said, because they would require having large concentrations or highly concentrated solutions in vitro. And our experimental techniques are not yet so sophisticated to understand, say, protein folding in highly concentrated solutions. But also in simulations, we usually we model the systems with, say, one polymer chain or a few polymer chains or one protein molecule in the system and try to study the effects. So it's more like you can see that there's a single child in the swimming pool. That's the level of our understanding, because our models that are developed, they are developed keeping in mind dilute solutions. Then and these systems comprise of millions of atoms. So earlier it was not possible to actually delve into such problems, but now, given the increasing computational power and resources that we have, simulations can actually play a very important role in modeling such systems and try to understand, give insights so that new experiments can be performed. So what has been known till now regarding macromolecular crowding? So the widely accepted theory is given by Asakura Osawa, who tried to explain colloidal aggregation in a solution of crowded polymers. So in 1950s, they observed this effect that if you put two colloids, big particles, in a crowded solution of a neutral polymer, say polyethylene glycol, these colloids would tend to aggregate and they tend to form compact structure. So this they explained based on depletion attraction. That means there is some kind of attraction happening between these big colloidal particles because of some depletion effect that is induced by the surrounding crowders. So what it means is that if you can see in this animation that there are dotted lines around the sphere. So basically it means that each molecule in the system has a size and has an associated volume that cannot be occupied or accessed by the solvent or the other molecules in the system. So we call this as solvent excluded volume. So now when these two big particles are lying apart in the solution, they occupy large volume, because of which the other space is limited for the rest of the molecules. This is highly unfavorable. But when they actually come close to each other, there is some interaction between these macromolecules, and the total solvent excluded volume of this aggregated structure is much less than what would have been when they were separated. Because of this, there is enough configurational volume for the rest of the polymers in the solution to move freely around, and that leads to an increase in the translational entropy. And this is entropically favorable process for this compaction or aggregation to happen. So this is how the polymers tend to deplete from the solvation shells of the colloids, and this leads to attraction between the two large colloidal particles. So this is what is called the depletion attraction, which is an entropic effect. And why is it only entropic in nature? Because the main underlying assumption of this theory is that there is no attractive interactions between the polymers or the crowders and the colloidal particles that are in question. And this is a very, very big approximation, because we know that in a living cell, there are charged biomolecules. There are sugars, there are proteins which have charges. So we cannot always assume that they will not have interactions amongst each other. Or when I say interaction, I mean soft interactions, energetic interactions, or attractive interactions. Also, I show here an equation, which is the change in the free energy when the macromolecules or the colloidal particles, they collapse. And you can see that it is proportional to the ratio of the size of the colloids over the size of the crowders, that capital D over small d, and also depends upon n, which is the packing fraction of the crowders. So this theory is pointing out to the fact that the free energy or the thermodynamics that are underlying such processes, they are directly related to just the size or the excluded volume of these particles and the crowders. So these are the main assumptions, but we want to assess these assumptions because recently some studies have pointed out that crowding effects may not necessarily always lead to compaction or aggregation of macromolecules. It has been observed in one of the studies where they studied a small protein, ubiquitin, and they studied the folding and unfolding equilibria in a crowded solution of dextran sugar, where they found that the protein starts to unfold as the packing fraction of crowders is increased. And as you can see, this is the change in the entropy, which is positive on unfolding, which is highly favorable process. So this actually led us to question that do crowding effects always lead to compaction or folding of the molecules, macromolecules? Also, in another study, they studied a small protein vilin. Again, they kind of studied the size of the protein as a function of another collective variable that describes the size of the protein. And at a very high concentration of crowders, which is the C5, they observed some non-native structures of protein along with the compact ones. And this again indicated that if the crowding effects may not necessarily always lead to compaction. So there may be some role of other thermodynamic forces other than entropy, which is energy, that may tend to play some role, which we do not understand completely till now. So this also shows that mostly till now the studies that have been done in this area, they make use of very simplified models where crowders, because Asakurasawa theory, as I showed you, just said that the free energy change just depends upon the ratio of the sizes of the crowders and the macromolecule in question. So usually people have modeled the crowding environment by big spheres or big ellipsoids, big rods, so that can induce these size effects of the crowded environment. But we now, when people have started doing atomistic simulations, we observe some different effects, and then we question ourselves that whether simplified or coarse-grained models are good enough to give us the comprehensive picture of these effects. So we ask these three questions. We just try to assess the traditional view, and we just ask that do macromolecular crowding effects always induce compaction of biomolecules? Can these effects be attributed only to size effects or the entropic depletion effects? And what is the role of soft interactions in these systems? We try to make use of molecular simulations, and we model the system using simplified systems again, and we make use of atomistic systems. So here we, how can we model a crowded environment, right? I showed you some examples where the crowders are like big molecules in the system where you just make them model as spheres. So you can imagine the crowded environment like a traffic jam where there are vehicles of different sizes. And one picture can be that we are, say, for example, we're trying to study how these two white vans would come close to each other in a jam-packed road where a lot of small cars are jamming the road. So this is something like where the size of the crowder can be modeled as less than the size of the macromolecule in question, for which we are trying to study the folding, unfolding, or compaction. And these crowders are known as nanocrowders, and many studies, recent studies have shown like that where co-solutes like urea and TMA or alcohols, they can also act as nanocrowders at very high packing fractions. Then the second scenario can be where in the traffic jam, all the cars are of equal size, and we're just trying to see, for example, we are trying to study some process where we are trying to study diffusivity of this red car in this jammed traffic. So here, this is a picture where the size of the crowder and the macromolecular is same. And third scenario, which is commonly used, has been commonly used, is when, for example, there is a big lorry on the road which has really taken up all the space and not allowing other cars to move around. So this is like where the crowder size is much, much, much bigger than the macromolecule size in question. So we try to model our systems. We just begin by modeling our system with the first scenario, where we take the size of the crowders a little less than the size of the polymer in question. So we try to understand, we try to understand these effects by studying the collapse equilibria of a very simplified polymer by keeping our crowders fully atomistic in representation and the solvent as well. So this polymer model has been developed by Bruce Burns' crew, where they have modeled this polymer such that it shows two-state behavior in pure water. That means it shows two minima in the free energy landscape of the conformations it can acquire. One is the collapsed state here, and the other is the unfolded extended state. So here, potential of mean force is just like your free energy of conformation change as function of the size of the polymer. And we make use of crowders. We model the crowders as small peptides. These are tripeptides, and this is trialanine, which is hydrophobic in nature. This polymer that we consider is Lennard-Jones polymer, 32 mol, and it does not have any charges. It only interacts via van der Waals interactions with the rest of the components of the system. We model water as explicit solvent, and also the crowders are atomistic representation. We perform umbrella sampling simulations and try to find out what is the free energy change of collapse of this polymer in different packing fractions of these crowders. But what we also do is that we want to study the role of interaction energy in such systems. So we tune the crowder polymer interaction energy by tuning the Lennard-Jones epsilon parameter. In one case, we make that weak, and in the other case, we make that strong. So please note, these are not charged interactions. When I'm saying weak and strong interactions, I'm still considering weak attractive van der Waals interactions, but we just make them weaker in one case and a little stronger in the other case. So we make use of Widom potential distribution theorem in its inverse form, which allows us to define the chemical potential change when the solute is added in a solvent. So what is the reversible work done when you add a solute in the solvent and then you switch on the attractive interactions of the solute with the surrounding solvent? So that reversible work can be actually... Sorry, is there a question?
No, there's some crosstalk from somewhere. Can the attendees just please mute their microphone?
Okay. So this reversible work, this Widom potential distribution theorem actually allows us to write a macroscopic thermodynamic quantity, which is the free energy change or the chemical potential change, in terms of a microscopic quantity, which is nothing but the polymer solvent interaction energy, which is phi over here. And if we expand this, we can actually also decompose this free energy change as something having the energetic contribution as well as an entropic contribution. And this energy is actually polymer solvent energy, and the entropy is the polymer solvent entropy. So you can consider this process as it's like a thermodynamic cycle where you solvate a collapsed structure in some solvent and try to find what is the free energy change. You solvate the extended structure of the polymer in solvent and you find out what is the free energy change. And when you subtract the two, you get the free energy change on collapse of this polymer. We also try to quantify this depletion effect that is traditionally known. So we can compute a parameter, which is again a thermodynamic quantity called preferential binding coefficient. It allows us to quantify the local excess concentration of the crowders on the surface of the polymer, which is with respect to that in the bulk. So it tells us how the polymer, how the crowders would adsorb on the surface of the polymer. And when I say adsorb, it's not only energetic interaction, it's the free energy. This gamma on this preferential binding coefficient gamma is actually related to the free energy change. And so it will have both entropic and the energetic effects. So what do we get? We try to compute, as I said, using umbrella sampling simulations, we try to compute this free energy change on the collapse of the polymer as a function of different packing fractions of the Crowder. So each point that you see over here has been obtained using set of umbrella sampling simulations, where each set of simulation has like 33 other independent simulations. So what we see over here is that it shows a very non-monotonic behavior, the free energy change. At very low concentrations, which are dilute solutions, which are not yet crowded, we see collapse of the polymer because the free energy change is negative. But as we increase the packing fraction, we see that the free energy change tends to become positive, which is something very different, because we expected that, since the traditional view of crowding effects tells us that it should always compact the polymer, or it should always collapse the polymer. But what we see at high packing fraction is that extended structures are more favored. And on the right hand side, this is the radius of gyration, or the size of the polymer, which also shows similar qualitative trend as the free energy change of collapse. And what was interesting is that when we compute the preferential binding coefficient, where the dotted lines are the gammas for the collapse state, and the solid lines are the gammas for the extended state. So this shows that if we keep on going from low concentration to high concentration, there is a reversal in the trend. First, the collapsed structures show higher binding of the higher absorption of the Crowders on the polymer, and then the extended structures start to show higher gammas or higher preferential binding of the polymers, which is also indicating how the collapse equilibrium shifts from the collapsed state to the extended state as we increase the packing fraction of Crowders. So in this case, because they're strongly interacting Crowders, we see nice adsorption of the polymers where they interact via energy as well as entropic interactions with the polymer. But what happens in the second case, where we have weakened the polymer Crowder interaction? We see that the free energy change is completely showing a different qualitative behavior. There is no non-monotonicity. There is always a decrease in the free energy as we keep on increasing the concentrations or the packing fractions of the Crowders. And this is what we actually had expected in the traditional macromolecular crowding effects, where we would expect that the collapse of polymer will be favored. And here, when we compute the gammas, they are all negative for both the collapse as well as for the extended state. What this means is that the Crowders or the peptides are completely depleted from the polymer surface in both collapsed and the extended state, but they are more depleted from the collapsed state. That's why the equilibrium shifts towards the extended to the collapsed state. So in order to understand whether this is an entropic effect or an energetic effect, we make use of polymer solvation energies and entropies, and we try to compute them and see what are the trends as a function of packing fraction of the Crowders. And what we see is that in the case of, if you remember the delta G plot that I showed you, it showed a non-monotonic trend, where at very low concentrations in this blue regime, it showed collapse, and at very high concentrations, there were extended structures that were favored. So what happens here is that if you look at the first point, that is in pure water. So it is known that this polymer collapses in the pure water by, say, I think the free energy change is -2 kilojoules per mole. Slightly collapsed structure is more favored. And this, if you decompose the energy and the entropy contributions, we see that energetically, it's a positive term. That means it is energetically unfavorable to collapse the polymer in water, because when it is extended in water, it has some favorable van der Waals interactions with water molecules. And when it has to collapse, it has to lose those interactions, which is energetically unfavorable. But because entropically, it is favorable because it releases these water molecules into bulk from the solvation shell. That is favorable, and that's why the change in the entropy is also positive, which compensates for the dehydration energy penalty that was there. But when we add more Crowders, as soon as we add the Crowders in the solution, we see that entropically it is also favorable to collapse the polymer. Also, it is energetically favorable. But when we go to the higher concentration regime, where delta G had become positive for collapse, that means unfolding was being favored, there we see that it becomes energetically favorable to unfold the chain. So here you see again the entropy change is positive, but please remember this is the entropy change for collapse. That means it is unfavorable for the unfolding. So energetically this process becomes favorable. In the case of weakly interacting clouders, we see that in the low concentration regime, the energy, the change in the polymer solvation energy is favoring the collapse, but at very high concentrations, the change in the there's a positive change in the entropy. The entropy change increases or it shows positive increase as function of the Crowder. So that means entropy is favoring the collapse of polymer at very high concentration. So this is what we see in the traditional depletion effect, that the Crowders are depleted as well as the entropy change is quite favorable, because when the polymer collapses, there is enough configurational volume for all the rest of the components of the system to move around, and that is highly favorable. So what is the take-home message from this work? We have got some insight, very nice insights from this very simple system that shows us that crowding effects may not always lead to compaction of macromolecules, although this is a very small polymer chain and also generic in nature. But we could easily see the role of the weak attractive van der Waals interaction in these systems, because when we tune the polymer crowded interactions, we see that polymer unfolds at very high concentrations when the Crowders are strongly interacting, have strong attractive interactions with the polymer. Whereas in the case of weak interactions, it's more like our traditional depletion effect, where we see the polymer collapses at all the packing fractions of the Crowders, and also it is an entropically driven mechanism. So we already have some insights. It's like an emerging view, or we already see some unexpected effects, and now we are doing some more work to understand, to change the type of polymer and to understand more types of Crowders with different chemical nature, to understand these effects in a better way. Because it is for sure that the size of the Crowders are important, but it is not the only important effect that should be considered. It must be an interplay of both the size as well as the energy of interaction that they have with the surrounding components of the system that are playing the key role. So this work was published recently in PhysChem ChemPhys. So if you're more interested to read about this work, you may refer to this paper. So I would like to thank the funding agency. So basically, I was formerly assistant professor at IIT Kharagpur at Center for Computation and Data Sciences, where I had started this work, had done most of this work, and I have also some funding from DST. Now, recently, I joined IIT Delhi in the Material Science Department, and our plan is to understand these effects and use them in nanomaterial self-assembly. And for this work, I would also like to thank Professor Nico van der Wet and Dr. Swaminath Bharadwaj, who have given really useful suggestions on the manuscript. And of course, I would like to thank the organizers for giving me this opportunity today. So I think I have finished within the time, so I would be happy to take some questions from you all. Thank you.
Thank you so much, Divya. We have time for a couple of questions from the audience. There are a couple in the Q&A box. I'll read them out.
Yeah, sure.
Maybe we can just start with them. So the first one is from Sriram. He says, in the cellular matrix, the particle sizes are comparable in your case, whereas in Usawa's theory, it's only applicable for particles and polymers which are orders of magnitude different in sizes. Can you please comment on this?
Yes. So yeah. So as I said that in this work, we cannot comment on the large size or the size effect of the Crowders, because we haven't used nano Crowders in these systems. As I showed, there were 3 cases how we can model the system. In Asakura-Osawa theory, it says that the ratio of the two, the macromolecule and the Crowders, the size of the ratio is important. So here it is comparable, yes, of course. So that's why in the next work, we are trying to, in the work, subsequent work, we are trying to increase the size of the Crowder as well as change the interaction energy between the Crowder and the polymer in the question. And we do see that the free energy change, trends in the free energy change are very different when the interactions are weak or strong, given that the size of the Crowder is much larger than the polymer. So in this present work, we have kept the size to be of little less than the polymer, because we wanted to rule out those effects for the time being and just look at the energy effects. That's why we use nano Crowders in these systems.
Okay, I hope, Shriram, that answers the question. And there is a follow-up question also, which says, in your simulations, Are all the entities coarse-grained, or is only the polymer coarse-grained and the rest all atom?
Yes. So only the polymer is coarse-grained. So this polymer bead is of the size of 0.4 nanometer, which is typically the size of CH2 unit. But the water is SPCE, and the trialanine peptides, they are Gromos force field. So that is united atom, where we just use CH as a sphere, basically.
I see. Okay. Okay. So we might have time for one quick question from the audience.
Hi, Divya.
Hi, Ravi.
I have one question. So here, when do you call it is this one as a crowder?
Sorry, when do we call?
Why do you call it a crowder?
Okay, because we are using very high, so crowder is, as I said, crowders can be small, large, or equal size molecules, which are densely packed in the solution. So if you look at the packing fractions of these systems, it goes up to 20%, which is typically what you also see in living cells. Of course, these are not very heterogeneously sized crowders that we can call this environment as a living cell environment. But because we are using very high packing fractions, so any small molecule like urea can also act like a crowder if you go up to a very dense packed systems.
Okay. So any foreign particle also will act as a crowder. Any impurities or
no, because they have to be at a very high concentration. So what do you like impurity, for example? Can you tell a little bit more about what do you mean by impurity?
I mean, any other polymer than the system.
So as I said, then they have to be densely packed. So they have to be at a very high concentration. So you can imagine we are doing some other work with dipeptides, and we have gone up to concentrations of say 400 milligrams per milliliter or 400 grams per liter. So that is the concentrations that we are talking about when we talk about crowded systems.
Okay. Okay. Thank you.
Okay, there is another one that Sriram has in the follow-up in the Q&A box. I'll just quickly read that out since this is the last talk. He says, how do you come up with the force field for the coarse-grained polymer and all-atom water trialanine? I mean, did you use some mixing rule for these interactions?
Okay, so in the case of the LJ polymer that we have used, this is the paper where they have developed this model. They have developed this model based on the fact that if they simulate this model in water, it will typically show two-state behavior, and it is also slightly collapsed in water. So they wanted to develop a hydrophobic polymer, so they wanted to show some collapse. That's why the parameters have been tuned or chosen in a way, the sigma and the epsilon for LJ, so that it shows collapsed structures in water. And in this work, I have used, as I said, this is Gromos. The tripeptides are Gromos force field, and this polymer is like we just define the LJ and the LJ parameters, bonded parameters, and angular parameters. There's no torsions in the polymer. And we use the normal Lorentz-Berth law mixing rules for LJ interactions, which I define the values that I have defined over here. And water is explicit water model, SPCE, that is well known. So, yeah.
Okay, great. Thank you so much, Divya. And with that, we come to the end of the session and the end of technical talk sessions for this e-SMYIM. So thank you to all the speakers again for giving us really exciting talks. And thank you to all of you in the audience for sitting through the entire session. We have a poster session coming up, I think, in 10 minutes. So maybe Alok or Sushmita, can I just hand it over to you?
Yeah, thank you, Kaushik. So first and foremost, this is the last session of this entire conference. So thanks to all the speakers who have been here today. And I know the last session is usually a little bit of the tight one, but I'm quite happy with the total turnout that has happened. So I think it's all kudos to the speakers, and of course thanks to all the session chair. Thanks, Kaushik, for taking care of this. And with this, we can end this last session. And now I will hand it over to Basa and Sushmita to conduct the closing ceremony. So Basa, Sushmita, it's over to you, please.
Hey, hi. Hey, thanks everyone for for attending SMYM for all the 3 days. I see that there are several names who were there throughout the 3 days. I think before we move on to so we have Jason and Udipta who took care of the poster sessions. So before we move on to the results of the poster session, I really want to mention that all the background work for SMYM 2020 was done by Alok and Sushmita primarily. Okay, we were just there, as a support, kind of very little push from our end. I think it was all their initiative.
That's not true, Basa.
That's not true.
No, let me finish. It can take. No, and also we also had a couple of postdocs, Somashri and as well as Virkeshwar, who really did a lot of job in making the program and also putting together the book of abstracts and sending out intimation to everybody. It does take a lot of organization skills to do that, right? So in that connection, I am very happy that the event was fairly well received. I think if I look at the numbers, I think at a particular day we had up to about 50 plus representation. So which is a good thing considering that it's an online event, and I'm sure people were occupied with a lot of other activities as well, right? So with so therefore, I mean, I think a big round of thanks goes to all the IAC team, the 2 young faculty and the 2 postdocs who really put together a lot of things. So with that, maybe I would like to call upon Udipta and Jason. Sushmita, do you want to add something, or should we just move on to?
We can move on to Udipta.
Yeah. Okay. Yeah, Udipta and Jason, can you just take the stage and then tell us about your opinion of the poster session, and some thought for the participants, what was good, what was missed, a few things that would be really helpful for everyone.
Sure, absolutely. And thank you, Professor Basa. And I would also, first of all, like to thank IIT Madras, team from IIT Madras, and also IISc. I know Alok very well, so I'd like to thank all the organizers for this wonderful conference and for giving me the opportunity. I have spoken in this conference for the first time, so it was a wonderful experience, and I think it was very well organized. So moving on to the poster session. There were 2 poster sessions, one on day 1, the second one was on day 2. So both me and Professor Jason from IIT Bombay, both of us were there and we judged the posters. I have to say that, I think I speak for both of us, and maybe all of us, I have to say that all the posters were very well presented. And this idea of, first presenting the video for 3 minutes and then followed by the question answers, I think it was a nice way to proceed with the poster sessions. And I think all the videos were very well recorded, posters were very well made, and I think overall the question answer sessions also went pretty well. The students were really good in answering questions. It meant that they understand what they're doing. It's very good, and it all, and and on the depth of and the wide variety of work that was shown in the poster session, it just shows how much work is going on in this community, and which is a very encouraging thing for all of us, I believe. So with that, I'll not show my face for too long. I'll just quickly announce the winners. I feel like one of those announcers in Oscars. It takes too long for announcing. Anyway, so so I'll just quickly lay out the marking scheme. So we marked both me and Professor Jason, we marked the posters in using 4 categories. So the first one is the clarity of presentation, for which we had 5 marks. The second category was the content itself, for which we had 10 marks. The third category was how the question answers were handled, for which we also had 5 marks. And finally, we had 2 marks for adhering to the time limit. So total 22 marks, and both of us marked based on whatever we perceived. And then finally, the overall score was an average of both of our scores. So both me and Professor Jason gave some scores, and the final score was an average of these two. And the good thing is that all the marks were final marks were in a very narrow range. There were a very narrow range inside which all the participants lied, and which is a very good thing. It means that everything was very close.
Like the monodisperse colloids?
Almost, yes. One relaxation time. So it also means that it was very difficult to choose so-called these rank holders. But since we have been tasked with this thing, we had to choose. We had to be a little bit ruthless and choose the first, second, and the third positions. And I just want to say that, I mean, whoever missed by a whisker. So it's not much. The difference is really, really small.
You should have asked RSC to have more prizes.
So I'll just announce maybe the rank holders. The first one, sorry. So I'll go in the reverse order. So the third place goes to Mr. Anuj Chabra from IIT Bombay. The second place goes to G. Manikandan, is from IIT Madras. And the first place goes to Marine Jose, who is also from IIT Madras.
No, IIT Bombay, I think, no?
It's written IIT Madras here. There might be a mistake in the...
No, she is IIT Madras.
Anuj Chabra is IIT Bombay.
Anuj Chabra is IIT Bombay, yes.
Yeah.
Okay, so those are the so-called winners. But again, I would just point out that it was very close, and as I said, all the final marks were in a very narrow band of numbers, within a narrow band of numbers. Okay, so with that, I'll sign off. Thank you very much, and over to you, Professor Basu.
Yeah, thanks, Sudipta. It was really nice. I mean, I knew that, in spite of, your busy schedule, both Jason and you were there for every poster and, asked questions when audience failed as well, right? So in that sense, you guys did a really fantastic job. And also the marking scheme, I think, was very well thought of as well. So I just want to add that, these places 1, 2, 3 is really not, if you're going to put this up in your CV, you don't have to really put first prize, second, and third. It's just a poster award which is sponsored by, Soft Matter, RSC Soft Matter, right? So that's how I would view it as. And I think we have also identified the next set of organizers for e-SMYIM 2021. The tentative date that we have fixed is, at least the month that we have fixed, is October 2021. That's what was discussed. And the people who are going to organize are going to be from IIT Bombay. There's going to be Sunita, who's at the Department of Physics, as well as Shobhana, who is also at IIT Bombay, I think Department of Chemistry. I don't see them here, but probably they may have some classes at this point. And they're going to be joined by a team from ISER Tirupati. And I see that Ravi is here. Ravi can say hello to everybody so that, hey, hi Ravi.
Hello.
Yeah, so Ravi is again at the Department of Physics, ISER Tirupati. So he said there's also a team of 4 faculty in the physics department itself. Plus, I know that there are a couple of faculty in chemical engineering as well who do soft matter. I think, so these are the 2 teams who are going to help out. And of course, there's going to be a participation or organization in terms of engineering representation by Danny, who's at the Department of Chemical Engineering IISc, as well as Priya, right? Priya. Yeah. I don't see her here. So yeah. So anyway, so that's the team that's going to handle. So I guess probably they're going to have somebody from the 2020 team as well, and they will communicate with everybody about the future course of action. And we would really like to thank all the invited speakers, right? Most of them really agreed readily to come and give a talk. We didn't have to really pester them so much, and I assume that everybody is at the fag end of the semester with PhD interviews and classes and everything. In spite of that, they were there for all their talks, as well as attended majority ones as well. And also, I think the poster session, I'm sure all the advisors pushed them in the last minute to really do this, because we had very few posters almost in the end. Okay, so in that context, I think the quality of the poster that were put together at that short notice was really tremendous. And that's one thing all the PhD students can be really proud of, that they could really make a very high quality poster given the very short time that they had for this event. With that, I'll hand over to Sushmita. Maybe she wants to say some words, and also the other participants. If you have any feedback for us or for the next SMYM team, what we could do better, what was missed, we would be very happy to hear as well. Sushmita, you want to take over?
Yeah, I just want to concur with whatever you said, Basa, that this has been a good conference, very good, like the quality of the talks were obviously very good, and the quality of the posters were also very good. So at the end, 3 got selected, but I would say that almost all the posters were of very high quality. So congratulations and keep up. So I guess we really need to work on how do we present our work, even if it's 2 minutes, how do we present our, like how do we give an elevator talk and so on. But if you have any comments or anything, please feel to put in the Q&A or raise your hand or just speak up. And thank you a lot for participating in the SMYM 2020.
I think we should also just quickly thank Dilip. He's not here, but he was instrumental in getting on the website and a lot of the initial legwork. He could not join.
Actually, now I see him here now.
Oh, he's there?
Just now I see him. Yeah, so Sriram says that, can you please include a workshop on some theoretical methods in the next edition? So Sriram, you should get a prize for actually asking questions for all the talks. Very good. Yeah, workshop on some theoretical methods. Even I would attend that.
Yeah, maybe on, because I'm sure that maybe we could, I think that's a good suggestion. So what we could do is we could maybe make a team of folks, who wants to put together maybe a workshop on simulation experiments, maybe particular techniques. I think that's a good suggestion. Maybe we should think about it. I think that's one way. Again, as Guru was mentioning yesterday, it's a good way to get connected, probably get noticed. Maybe invite some industry folks as well. I think that's a good suggestion, Sriram. So yeah, thanks so much.
So if I can add something, Basta.
Yeah, please.
So it's like something like the Gordon conference style. So they will have a 1 day a priori of the main conference, and that will be mostly students and 2 or 3 invited people, and there will be dedicated workshop style of lectures and discussions. Something like that can be arranged, or similar to APS also. APS also, the day before the main conference start, there will be workshops given by 1 or 2 faculties for 3-4 hours long duration, and most of the students reach to the venue a day before. So those things can be
Tarak, that's a good suggestion. One thing that we also have to keep in mind is, this Gordon conference is the people who get invited to give talks are really highly accomplished. I think, I mean, definitely we could do something of that sort in the Indian context as well. And probably once people graduate from, the young investigators to, maybe 10 years down the line, that could be some nice event which we could start as well. But considering that, a lot of folks who are, joining SMYM are at the initial stages, I think they would still be at an earlier stage of their.
No, I mean, Basa, what I'm trying to mean is that keep it as a young investigator meet, but the format wise, it's not the speaker wise. The format wise, there is a day before main conference start. There will be workshops where mostly students arrived a day before, and 2 or 3 faculty who will be organizing a workshop in a particular area, so they can arrive a day before. So the format wise, we can pick those format, not the speaker, or in terms of that we can keep as it is, our young investigator meet.
Yeah. Okay. Yeah. Yeah. I think that's a good point as well. Yeah. So yeah, we'll keep that in mind for, for the next future meetings as well. So maybe because Ravi is here, maybe he could take note of this, and then we'll see how that goes. Sure. Yeah. Anyone else who wants to have a quick word? I mean, tell us something about maybe someone from the attendees, the students who wants to speak up. You can raise your hands and.
I mean, I can have another word. So you just said that all speaker agreed to come and present the talk. I would say that we did not come anywhere. We just presented from our home comfort, and a big thank you for all 4 of you. Thank you.
But hopefully,
I would just like to add.
Yeah, please go ahead.
Yeah, I would just like to add what Tarak was suggesting. First of all, thanks to all of you for inviting me. This was my first time I attended this meet. So since it's a young investigator meet, we can also have a day or half a day only for postdoc presentations, because they are like early career researchers. That will also give them some platform to showcase their work if they are eager to discuss and connect with us. So that is something also we can think about in the next meet.
Yeah. So this time we had at least one postdoc presentation.
Yes. Right. So maybe more we can think about if there are some speakers eager to.
Yeah. So Divya, that's a good suggestion. We also have to keep in mind that, see, 2.5 days, we already have almost 24 people with in this session. I think there were 2 Inspire faculty and 1 a postdoc, right? That makes it 23 faculty and 1 postdoc. Now, of course, a fraction of the postdocs talks could be increased, and we could also have maybe a senior PhD students as well included as well. I think that's some logistics that probably people have to work out. The other thing is, I think we would also like to look at the kind of participation as well, right? If we at this particular meeting, I think a lot of posters also came out because we requested all the invited speakers and the organizers and everybody to really force the students to really come and again present stuff, right? Yeah, and I think that if you go for a more fraction of postdocs and PhDs for SMYM, I have a feeling that there could be drop in the the participation that one has to worry about. But yeah, I think your point is well taken. Maybe more postdoc and maybe a few senior PhD students would be a good addition as well. Maybe then we probably have to tweak a little bit with the duration of the conference as well. Maybe instead of 2.5 days to a little bit maybe more, or maybe have 1 session exclusively for postdocs, maybe 1 for senior PhD students could be one thought as well. Yeah, thanks for that suggestion.
So by the way, I just wanted to mention that the Complu is starting this Meet the Faculty Candidate session from this year, I guess. So they are already creating a platform where all the postdoc and who are looking for faculty opportunities. So they're organizing a session exclusively for them. And whatever we do, we just maybe we can think those aspects also, that there are other platforms and more senior people also come there. So we can keep that in mind.
Yeah, I think, I mean, because see, I think the post seniors, PhDs would be a good idea. But in terms of the early career and all that, I mean, or people who are trying to get into a position, I mean, in most cases, all of us know that we won't be so much part of the, selection committees and things like that, right? So in that context, I think the early career or people who are really looking for a faculty position kind of stuff, I think we should leave it to the meetings like Conflu and maybe the ones where more senior folks go as well. So, yeah. Hey, Dilip, do you want to add something?
No, I just want to say that what Tarak said makes sense, because see, adding few postdocs is okay, but I think our primary focus is on the young investigators who already have a job and try to have a network in India. I think for postdocs there are many other platforms. If we have Conflu just lined up next to this, so we can certainly try to improve it a bit. But given the constraint of 2.5 days, it may be a little difficult to include many PhD and postdoc in the speakers list. And that's what. But is there a decision on this internationalization? Did we decide anything on that? Like the next one, maybe we can try, or every other year.
So yesterday it was discussed that it's going to be in October.
Okay.
Yeah, maybe I mean I think the organizers of the next one should really think through, and then
we have a
lot of time to worry about.
I think Ravi is here, so you can think of to start with one or two. One can think of.
Yeah, sure. We can have a short session with the international speakers.
Yeah, then a good idea. Bring it in.
Yeah, I think the keynote speakers, then when they spoke about what are like Professor Sanath had spoken about the second part of the talk where he told us about the challenges and how we should publish and all those things. I think that was very, very helpful and insightful for all of us. I think everybody would agree. So if we can have such sessions from senior professors who are experienced in this field, that will be really good. In the next conference also, that will be really good.
That's very good, Dibya. I think we should kind of keep that in mind. Always have one talk in those directions. Being a senior professor and then giving like that, like this to them, so that it's not fully focused on that. Little bit going on other aspects of career.
Right.
Yeah. Yeah. So. Alok, do you want to add something?
No, I think those are good suggestions. They can all be taken up by the next organizers. We always had a time constraint because I think the critical mass for soft matter people has increased in India. So you have a lot of young people who are just starting out as faculty or quasi-faculty like BFC Inspire. And so we need a platform for them to get together. So it's going to be a challenge for the next set of people who are organizing. So we can always help them out if they have. But let's see how the next year turns out. I'm looking forward to the next year.
We definitely need a big push. We are organizing for the first time. We definitely need your help, suggestions, whatever the capacity you can.
Yeah, I think that, like Alok said, I'm sure all of us would be there to help you guys out. I don't think you should really have to worry about that aspect for sure. So, yeah. Okay, so then maybe it's a time to close. Yeah. Okay, sounds good. So thank you everyone for the wonderful meet.
I think Alok and Susmita has done good work. We should.
Yeah. I mentioned that already.
That is not
okay. and
all of us can unmute and clap.
We should have a screenshot. We'll put it in the website later on. If we switch on the video, and
we should have taken we should have asked everybody to turn on their video and then
take a screenshot
and then put it on SMYIM.
You can still do it now.
Yeah, I'm joining the mobile, so I can't do it. Somebody else
I can do it.
Yeah, good.
Check how
you can take the screenshots. That's easy thing.
So you can put one in the website, to have a memory.
But can all of you please turn on your fan just for a second? And keep it on a little bit, and so that we take a snapshot.
I'm just promoting everyone to the panelists so that you know.
Okay, let me do that.
Yeah.
Okay. So Alok has a lot of mass there on the one screen.
We are social distancing.
It's good.
Virkeshwar, your camera is still moving.
Virkeshwar,
The camera is on. Okay. But still all the blocks are not filled up yet. So I'm just waiting.
Ashok and Udipta as well.
Ashok, please switch on your video if you want.
Just for 1 minute.
Yeah.
Ashok.
Ashok, Rumia and Udipta. Okay, I took a snapshot. But I just took a print screen. I don't know of a better way of doing this.
That's good. I think that's also okay.
Done.
Good. Thanks.
Thank you.
Thanks so much. Yeah, we'll see you all in 2021. Yeah, October.
The new year.
Yeah.
Hopefully everything will end.
Yeah, maybe in person. Who knows?
Yeah, sure.
Vaccines
Okay,
are.
bye-bye.
Bye.
Thanks.
Bye-bye.
Bye.
And nice to see you all. Bye.
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 Okay, we exit then. I'll end the meeting.
Yeah, look.
We are looking forward to the next one with your help.
Yeah. You can contact us if you need any information.
Yeah, sure.
Yeah.
Okay.
Yeah.
Okay, bye, Ravi.
Bye.
Bye, Alok. Bye, Ravi. Bye, Basa. Bye.